three group of bars. If you observed in graph, they are representing RGB color space and performance of RGB color space for 7 machine learning algorithms and 9 ensembles. Middle three groups, if you observed with LUV at the base, they are performances of Kekre's LUV color space when BTC were used as features, and at the end we are getting YCBCR color space. Overall, if we observe what is the highest peak, then we may say that LUV color space with L1 and L2 fusion is giving us better performance for some ensemble which is blue shaded, which is AD tree, random forest and SVM. So this is giving us highest accuracy among all the experimentation which we have tried. In generic, if we observe RGB level 1, RGB level 2, level 1 and level 2 if taken together are giving us higher accuracy values. If we take LUV level 1, LUV level 2, level 1 and 2 when taken together they are giving us higher accuracy values. Same thing is observed for YCBCR level 1, level 2, when level 1 and level 2. So feature level fusion is appearing to have worked in BTC case with all the color spaces. If we observe level 1 of RGB and compared it with level 1 of LUV compared with level 1 of YCBCR, we will say that LUV and YCBCR has given us higher performance than that of RGB color space. So one of the research questions whether luminance chromaticity color spaces are better is giving us positive assertive answer. Yes, they are better than that of conventional RGB. And the best accuracy overall is observed by ensemble of AD3 random forest SVM with LUV color space in fusion of L1 and L2. So here fusion perform better and luminance chromaticity color spaces perform better. If we compare individual machine learning classifiers with ensembles, we have observed that ensembles are performing better than that of individual machine learning algorithms. Same thing we observed for TSBTC accuracy, Thepade sorted block truncation coding. Here also the observation, if we'll take RGB L1, L2, L1 plus L2 is giving us better performance in RGB color space. So feature level fusion is performing better. Same trend is observed in LUV color space and in YCBCR color space. Last three groups of bar graphs are showing us YCBCR color space, L1 plus L2 is better. Overall, if better performances to be or best performances to be observed, again the ensemble, same ensemble, AD3, random forest and SVM was performing better here with YCBCR color space and also in level 2 of TSBTC. So this was surprise that TSBTC level 2 is performing better than that of other possible combinations. Same thing was observed for fusion of BTC and TSBTC features for level 1, for level 2 and level 1 and level 2 all fusions. Here also we observed that luminance chromaticity color spaces are performing better. The ensembles are performing better. Here little different ensemble has given us highest accuracy, and level 2 feature fusion of BTC and TSBTC have performed better. So feature level fusion was working here as contrary to that of TSBTC and similar to that of BTC. Same kind of trend was observed in sensitivity with reference to block truncation coding. Again here luminance chromaticity color spaces were performing better, ensembles were performing better, and the fusion was performing better than that of individual levels. TSBTC similar trend was observed. When we took fusion of DTC and TSBTC, even in sensitivity, same kind of trend was observed. In case of specificity, the trend was little deviating. The trend which was observed in case of accuracy and sensitivity was not observed in specificity. But as right in the beginning I said, here sensitivity was mattering more than that of specificity. If average across all variations have to be taken for accuracy, sensitivity, specificity for RGB color space, LUV and YCBCR color space, in accuracy, the luminance chromaticity color spaces like Kekre, LUV and YCBCR were outperforming to that of RGB. Same was observed in sensitivity, but in specificity, RGB was performing better. If when we took average across these three performance matrices, we observed that in average, because sensitivity and accuracy are following same trend, LUV and YCBCR were performing better over RGB. So luminance chromaticity color spaces were considered to have given better performance because they were able to identify melanoma as melanoma with better capability. Similarly, when we tried comparing level 1, level 2 and fusion of level 1 and level 2 for BTC, for TSBTC and for combination of BTC and TSBTC with reference to all other variations in average accuracy, we found that here BTC level 1 and BTC level 2 is performing almost similar to that of TSBTC level 2. BTC level 1 and 2, when are fused together, the feature vector size is much bigger than that of consideration of only TSBTC level 2, where feature vector size was only 9 elements. Here it was 6 plus 12, 18 elements. So the performance variation was not that much when a TSBTC is just half of the size in feature vectors as that of fusion of level 1 and level 2 of TSBTC. Accuracy, sensitivity was giving same trend and average specificity was almost giving similar trend. When average across all matrices were taken, we found that BTC level 1, level 2 fusion and TSBTC level 2 only are performing better. So TSBTC level 2 was considered to be better because it had half the number of feature vector elements as that of combination of level 1 and level 2 for BTC. The top 10 performances with reference to sensitivity, specificity, accuracy were obtained, and with reference to average across all matrices, the descending order or of performances was mentioned here. So AD3, random forest and SVM were supposed to have given better performance for melanoma skin cancer identification when used in YCBCR color space with TSBTC level 2. Carefully, if we observe that TSBTC level 2 has given better performance in 5 of the top 10 performances, LUV and YCBCR color space have given almost similar performance, but LUV being computationally lighter, we may go ahead with LUV color space, and ensembles have performed better than that of other machine learning algorithms, especially SVM, random forest and AD-tree when taken together have given us better performance. So all these three performance measures are given equal importance, and we came to conclusion that AD-tree, random forest and SVM should be used as ensemble here with YCBCR or Kikri's LUV color space, and feature fusion is not supporting much. TSBTC level 2 features are giving us almost similar performance. So the earlier asked research questions were whether ensemble performs better than individual machine learning algorithm. The answer is yes. Which ensemble is better for melanoma identification? So we may say now AD-tree, random forest and SVM is supposedly giving us better capability of identification of melanoma skin cancer. Total 3 color spaces were used, and we wanted to find out whether luminance chromaticity color space is giving better performance. The answer is yes. And which color space gives better identification? So YCBCR gives better identification, but it is slightly better than that of Kekre's LUV. So Kekre's LUV being lighter in conversion, we may say that LUV is performing better with reference to computations, and with reference to accuracy, YCBCR is performing slightly better. Total 7 feature extraction methods were used, and we wanted to identify whether feature level fusion is better. So to some extent in block truncation coding, feature level fusion was performing better, but overall TSBTC level 2. So in TSBTC, the feature level fusion did not perform, but TSBTC level 2 individually was giving us better accuracy. So thus 7 machine learning algorithms with 9 ensemble combinations were tested. 3 color spaces were considered, and features were computed with BTC and TSBTC. Finally, in conclusion, we may say that ensemble is performing better, and overall best performance is given by AD-tree, random forest and SVM. Ensemble with majority voting logic in YCBCR color space for Thepade sorted BTC features of level 2. With this, the melanoma explorations were done, and the paper has got accepted in Inder Science, IJCVR, International Journal of Computer Vision and Robotics. And the paper is very much can be seen in forthcoming articles. Very soon, maybe in 2021, by April, it will get published and it will be available online for reading. The second explorations which we attempted was about glaucoma identification from fundus images. Again, using Thepade sorted block truncation coding, because we found that rather than BTC, TS-BTC is performing better. So we have thought of using this TS-BTC and using it with help of now multi-layer perceptron, convolutional neural network architecture for glaucoma identification from fundus images. If glaucoma and funding are too much of Greek and Latin terms, I will try to simplify that glaucoma is a disease of the eye in which the fluid pressures present in the eye get imbalanced. If you look at left hand side image which is present here, healthy eye and eye with glaucoma, look at this portion, especially the blue region. The fluid which is present in healthy eye is almost uniform, and some sort of imbalance can be observed in eye with glaucoma. What this imbalance does is, it imbalance causes extra pressure on the fundus. Fundus is rear part of our eye image, and that may impact the loss of vision. If this cannot be cured again, but if this is unattended, a person may lose vision completely. The growth of this glaucoma can be limited and restricted by medication. So also early detection is very important in case of glaucoma, as that was in melanoma skin cancer. If we want to save the vision, especially in diabetic patients, the occurrence of glaucoma is more frequent. The main type of glaucoma are open angle and close angle. Age, thyroid problems and diabetes are mainly risk factors for glaucoma, and symptoms can include severe eye pain in some cases. Treatment includes surgery and medication to stop the growth of glaucoma. For a layman's view, first images in first column on left hand side are normal vision. Then person may not realize, but he may start losing his vision. So in early stages of glaucoma, the vision which a person would have would be something which I have shown in both the images in the middle column, where on the edges you will find some black region getting created. So that is restriction of your vision due to imbalance of that fluid. And in advanced stages of glaucoma, you could observe that the further vision loss will be observed, and a normal person which is able to see the scenery like first image, a glaucoma, advanced glaucoma stage, will be able to see only restricted part of it. If it is still kept unattended and unmedicated, further complete vision can be lost and it cannot be recovered again. So this is one of the severe problems. Fundus images are used for glaucoma identification. There are special fundus photographic cameras which are present with the eye practitioners and eye surgeons and the doctors. And the images which are taking the rear portion of eye are generally called as fundus images, and these cameras are called as fundus cameras. They have some intricate microscope attached to a flash enabled camera, and they can take the photographs of rear portion of eye. So first four images on left hand side are giving you idea about normal images of fundus portion of eye, and right hand side four images are giving you the eyes with glaucoma developed into it at various stages. So just looking at the images as a layman, we can just see the thickness of the white portion is or the enlargement of the white portion is indicating presence of glaucoma, but it needs actually experts, and only experts can identify the growth of that glaucoma and accordingly start the medication and advocate whether to go for surgery or not. Again, Thepade sorted block truncation coding, TS-BTC was used here. If you carefully observe these fundus images, there are some black portions on all sides of the images. While processing these images, all these black portions were removed and the remaining portion, which is actually capturing the texture of the fundus of eye or rear portion of the eye, was only considered for feature extraction. So all these black pixels were removed and only this region of interest was taken. On that region of interest, we obtained red, green and blue planes because all these were color images. The respective planes were converted into one-dimensional arrays. Those arrays were sorted in descending order. And after sorting, they were divided into 2 parts, 3 parts, 4 parts, 5 parts, 6 parts, and 4-part averages were taken. So TSBTC 2 array was giving us 6 feature vectors. TSBTC 3 array was giving us 9 feature vectors. TSBTC 4 array was giving us 12 feature vectors, so on and so forth. In case of multi-layer perceptron, it is class of feed-forward artificial neural network. And multi-layer perceptron consists of minimum 3 layers. There can be multiple number of hidden layers. How many number of hidden layers should be there was one of our research questions. Then which level of TSBTC will be giving us better accuracy in fundus or glaucoma identification from fundus images was one of the curiosities which we had. And MLP, multi-layer perceptron, is fully connected network. It has input layer and it has output layer. So it follows supervised learning logic with back propagation. So errors can be corrected by adjusting the weights unless and until desired accuracy is not obtained. And generally a data which is not linearly separable, which is not very clearly separable, can be classified using multi-layer perceptron. So again, fundus images were considered, or the problem of glaucoma identification was considered as a classification problem. And we wanted to classify images into with glaucoma and normal fundus images. There are 2 data sets which are available. Both were used for this experimentation. Refuse data set is available with 800 fundus images. And there is one created by IIT Delhi, which is Drishti. Refuse is freely available on net. For Drishti, we need to write to IIT Delhi and we need to get access of these images, and they do give us for research purpose. So the Drishti had 100 fundus images into it. In experimentation, as I said, how many number of hidden layers have to be taken in multi-layer perceptron? Based on number of hidden layers, the performance may vary. So we have decided taking around 40 variations of number of hidden layers, right from 5 hidden layers, 10 hidden layers, 15 hidden layers. With increment of 5, we went up to 200. And we wanted to check which number of hidden layers are giving us optimal performance. In this case, higher the number of hidden layers, more will be the computation cost. Lower the number of hidden layers, lesser will be the computation cost. But generally people say higher number of hidden layers do give you better accuracy up to an optimal level. So that optimal level we wanted to obtain. 2 data sets were used, Refugee and Drishti, and 9 feature vector extraction methods were used. TSBTC 2 array, 3 array, 4 array, 5 array, 6 array, 7, 8, 9 and 10. Why did we stop at 10 array? That will be coming shortly while seeing the results. But 2 array was simply sorted arrays divided in 2 parts. 3 array sorted arrays divided into 3 parts. So on and so forth. At 10 array, sorted array was divided into 10 parts. So total 360 variations of proposed method were tested on 2 data sets here. Obviously, the research questions were what number of hidden layers will give us optimal performance, and will the optimal number of hidden layers be found across both the data sets, or can it be data set specific? Then total 9 feature vector extraction methods were used, and which level of TSBTC, Thepade sorted block transition coding, is giving us optimal performance for glaucoma identification, and is it same across data sets? Were the interesting things. Now, if you look at first column, though visibility is little issue in this table, but first column is indicating number of hidden layers. Each row is giving us accuracy for, say, first row, 5 hidden layers for TSBTC 2 array, second column, TSBTC 3 array, third column, and TSBTC 10 array, second last column. The last average column is giving us idea about performance of that hidden layer across all these feature extraction methods. And the last row is giving us idea about maximum accuracy observed by respective feature vector extraction method. Second last row is giving us idea about average of accuracies for respective feature vector extraction methods across all hidden layers. So carefully, if you observe the last column, you will find in 20 hidden layers, the performance is highest, which is 90.61. And carefully, if all columns are observed and second last row of average is observed, you will be getting that TSBTC level 10 and TSBTC level 3 are giving us, level 4 are giving us better performances. So graph was plotted like this, and it was only jumble of all feature vector extraction methods. Their accuracy is plotted across number of hidden layers. So nothing was coming out of this graph as observation. Finally, we decided taking average across the number of hidden layers. So second last column of average was plotted in this graph, and we found that TSBTC 3 is performing better in refuse data set, closely followed by TSBTC 9 TSBTC 10 So for refuge data set, TSBTC 3 was performing to be better. Then for refuse data set, when hidden layers were compared across all feature vector extraction methods, we found that global maxima is observed with 20 number of hidden layers with accuracy 90.61, closely followed by 5 number of hidden layers with accuracy 90.5, and second best performance is shown by 170 hidden layers with accuracy 19.39. So optimal performance in refuse dataset was observed with 20 hidden layers with TSBTC 3 closely followed by 9 10 and 8 Same thing was done for Drishti dataset even, and for refugee and Drishti the average was taken across the datasets. So when average is taken across the datasets, we found that TSBTC 7 is giving us better performance across both the datasets as averaged out across these datasets. For sensitivity, for specificity, as well as for accuracy, it was giving us better performance. So the answer to our research questions was whether number of hidden layers, which number of hidden layers are giving us better performance or optimal performance. Across both datasets, surprisingly, 20 number of hidden layers in multilayer perceptron were giving us better performance, and optimal number of hidden layers were obtained as 20 in multilayer perceptron. And which feature level extraction method is better? So TSBTC 7 was supposedly performing better across both datasets when averaged out across both datasets. So 40 hidden layer variations were experimented, and we found that the 20th hidden layer is giving us better accuracy, and 9 feature vector extraction methods of TSBTC were tested, and TSBTC 7 was giving us better performance. That was all about the glaucoma experimentation. The experimentation on glaucoma are still going on, and we could not come up with any research contribution in that in form of publication, but the efforts are further going on, and we are exploring further things with the help of machine and deep learning into glaucoma identification. The third part of my presentation is COVID-19 identification from chest X-ray images using in earlier cases in glaucoma as well as in case of melanoma, the dermoscopic skin images were color images. They were multichrome images. Even in glaucoma, the fundus images were color images. While if you observe X-ray images are mainly grayscale or monochrome images. They are not color images. So the features like BTC, color BTC or Thepade sorted block truncation coding, we found may not be appropriate for X-ray image feature extraction because they are not multichrome in nature. And hence we have decided to go with conventional local binary pattern, though computationally they are little heavy, but for local binary patterns for understanding the X-ray images. And COVID-19 we all know is declared as pandemic by WHO, and since last March everybody's life is withheld because of this COVID-19, and till there is pandemic which is going on, we don't have end of COVID-19. The problem with COVID-19 is the symptoms are very much similar to that of pneumonia or normal flu, and hence it becomes very difficult to identify COVID-19 in early stages. with patients having comorbidity. If COVID-19 is detected early, then we can simply save lives. Otherwise, it becomes fatal, and we all have witnessed that thing. So carefully, if you observe in figure, there are 3 rows: row number 1, row number 2, row number 3. In row number 3, the X-ray images having pneumonia are taken. In row number 2, X-ray images having normal lungs are taken. And in row number 1, X-ray images having the infection of COVID-19 is taken. We need expert doctors for classification of these 3 X-rays into pneumonia or COVID and normal versus infection. Again, in pneumonia, we can have viral and bacterial infection. The data set of these images is taken from archive and it is available on GitHub even. It was created by these gentlemen, Cohen, JP, Morrison, and COVID-19 image data collection. If you search on Google, you will be able to get this data set. This was lastly referred on 10th May by us. Local binary patterns are very unique texture descriptors. At the bottom, if you see, some texture in grayscale is observed in the image. If I take a small patch of size 3 by 3 from this image, as I've enlarged that patch here, that patch will have intensity values. Now what LBP does, it takes center value of intensity, which is 54 in this given example. It compares this 54 with all its neighbors. Now neighbors at distance 1, distance 2 or distance 3 can be considered. So this distance from the center pixel is called as R, or the distance, and how many number of neighbors have to be considered. Here if we consider all neighbors which are at distance horizontal, vertical and diagonal 1 position away from the center, my distance or radius will be 1 and number of neighbors will be equal to 8. Likewise, we can decide how much should be distance and how many neighbors have to be considered. For this example, where distance is 1 and neighbors are 8, 54 will be, or center pixel value will be compared with all its neighbors. If neighboring pixel value is equal to or greater than the center pixel value, it will contain 1 in their respective position, else it will contain 0. So because this 85 is greater than center pixel value 54, this position is containing 1. Because 21 is lesser than 54, this is containing 0. Once these zeros and ones are obtained, in a particular direction, these zeros and ones will be read out. Here they are read in this direction starting from this position. So 1100, 1011. This binary vector will be converted into its decimal value 203. And this 203 will be represented in the same center pixel position at same row number and column number in the output binary pattern image. So the image of same size can be obtained using LBP applied on that image, but that image will be representing local binary patterns with radius or distance equal to 1 and number of neighbors considered equal to 8. This process would be repeated for all possible 3 by 3 pixel windows which can be enclosed within the limit or boundaries of this image. And at every center pixel value, we will be computing a new decimal value which would be representing the binary pattern of the intensities which are present. So this necessarily gives us texture. How many neighbors have to be considered and what distance should be considered, that can be decided based on whether we want coarse texture to be represented or superfine texture to be represented. And image can be seen as composition of micro patterns which can be described using this local binary pattern operator, and operator works in this way. So one of the best performing texture descriptors so far is local binary pattern, and it is very widely used in the applications where you want to classify, you want to discriminate the textures or the representation of pixel intensity values present in the images, and you want to use it in some or the other application. LBP operator was originally designed for texture description only, but then later this texture descriptors got utilized in classification and identification problems. So the idea was simple, that for every chest X-ray image, we wanted to obtain the texture of that image, but texture itself may not be used for classification. Instead of using it for classification, we have decided to convert that texture pattern obtained or LBP image obtained into set of features, and here histograms were taken of that LBP, quantized histograms, and those histograms were taken as features further for chest X-ray image classification into COVID-19 versus non-COVID-19. So the idea was take chest X-ray images, obtain their local binary patterns with reference to how many, at what distance the neighbors have to be considered. So for r equal to 1, 2, 3 up to r equal to 10, various number of neighbors were considered. For example, if distance 1 and 8 neighbors have to be considered, then these 8 neighbors will be considered as shown in first grid. If I want to consider 12 neighbors at distance 2, this was considered. Then at distance 3, 12 neighbors, this was considered. So for all these combinations, the local binary patterns were obtained, and those local binary patterns were converted into quantized histograms. Those histograms were used as feature vectors to train the machine learning classifiers, and these classifiers were further used for classification of images. So here in experimentation for local binary pattern, we have considered 9 different combinations of what should be the distance of neighbors to be considered and how many neighbors have to be considered. So the respective RNP combinations for distance 1, 8 neighbors, the example which we have seen, distance 2, 16 neighbors, up to distance 10, 80 neighbors we went. The machine learning classifiers used were support vector machine, naive Bayes, k nearest neighbor, random tree, and 3 ensembles created out of these 4 classifiers. The logic of selecting these 4 classifiers, because in conventionally in literature, the similar kind of attempt people have done using one of these classifiers, but for classifying the chest X-ray images into pneumonia and normal. So that was extended further for COVID-19, and total 70 variations in experimentations were observed. So in local binary patterns, 10 variations were done. If I am taking less number of neighbors and small distance, then I may say fine texture will be observed, and here coarse texture will be observed. So which granularity of local binary pattern or texture is giving us optimal performance for COVID-19 identification capability was interesting to see, and which coarseness or fineness will be giving us better performance. Out of 5 machine learning classifiers and 3 ensembles, which classifiers and which ensembles were better, that was interesting to see. Accuracy, along with accuracy, positive predictive value, which is precision, was taken. In this case, the data set was mostly imbalanced because we had very few images of COVID-19. So only accuracy would not have sufficed the requirement, since we have taken F major and MCC value for performance comparison. The performance comparison was done across all combinations, and finally we could observe that R is equal to 1 with P is equal to 8 is giving us better accuracy for COVID-19 identification. Highest accuracy is achieved by ensemble, random tree, random forest, and KNN for R equal to 6 and R equal to 7. So distance equal to 6 and 7, or radius equal to 6 and 7, which is 89.180 as looking at the average. Same thing was observed for PPV, same thing was observed for sensitivity, F major, MCC values even. And if you take average across all these performance measures, we found that random forest is performing better. The ensemble of random tree, random forest, and KNN is giving us better accuracy, and ensemble learning is better than that of conventional individual machine learning. So the granularization with radius equal to 6 and 7, or distance equal to 6 and 7, with number of neighbors respectively equal to 48 and 56, were giving us better classification accuracy for COVID-19 chest X-rays from that of pneumonia or normal X-rays. Random forest machine learning classifier was better, and the best performance is observed by random tree, random forest, and k nearest neighbor ensemble combination with majority voting logic. So the conclusion was chest X-ray images we were able to classify, thus more things need to be done. This initial exploration got published in IEEE Bombay section signature conference, and where this was one of the papers out of the 4 which got best research group. award conferred onto it in 4th and 5th December. Further explorations on this COVID-19 are going on. Many thanks for patient listening. And if you have any questions, I will be obliged to answer.
Yes, sir. Thank you, sir. This is Dr. Sakshi Paitani. Good morning, sir.
Very good morning, ma'am.
So I have few questions. Actually, the complete session was like question and answer. So whatever I have listed under the questions, you have already answered.
Okay.
So I have 2-3 questions. So may
Yes,
I proceed, sir?
yes, ma'am. Please, ma'am. Thank you for compliment. Please proceed.
So one of the participants want to know for maybe you have answered this for glaucoma detection, which features have used in research work?
In the research, even in glaucoma, people have tried using, see, for handcrafted features, they've used GLCM, gray level co-occurrence matrix, which are also called as Haralick moments, and they have tried using local binary patterns and variation of local binary patterns as local ternary patterns. And wavelet transforms are mostly popularly being used. We have explored using TSBTC, which is computationally lighter than all these things. I hope that has answered the question. And
yes, sir. Yes.
in deep neural networks, we have to extract features. So various neural network architectures have been used for glaucoma detection in literature.
Okay. Thank you, sir. Could you please explore research area in biomedical on the same track?
Yeah, see, when we talk about hematology images, much less attention has been paid to hematology images, especially images related to blood cells, and microscopic images and such data sets are available in abundance, and those would be interesting areas to work with. Apart from these, MRI, CT, you take any modality of medical imaging that would be related to biomedical image processing applications and research area.
Yes. Thank you, sir. One more question is there. Does ensemble algorithm perform better than DLCNN in unbalanced data?
In CNN, unbalanced data set may give you, little favorism. So the network will get trained for, will get better trained for more number of samples which are available. So if the data set is highly imbalanced, then DCNN is not advocated. There you should go for machine learning algorithms, and ensemble always perform better than individual machine learning algorithms in most of the cases. But if the data set is balanced and if number of images are available in very good number, then you should only try for DCNN.
Thank you, sir. So with this, okay, one more question is there, sir, from Mahendra, sir. If diabetic retinopathy using fundus images are used, whether it gives accurate result as compared to manual detection method of diabetic?
See, in case of scarcity of doctors, diabetic retinopathy checks the effect of diabetes on eyes. So that is totally different than that of pathological verification of level of diabetes, which is done through blood tests. So these two could not be compared. And in case of fundus images, yes, expert doctors cannot be replaced. But in case if expert doctors are not available, and if we want to come up with some app which will be giving us prior idea, looking at the images, then it is okay.
Thank you, sir. So, yes, so no more questions from the participants, sir. Thank you, sir.
Thank you, organizers, for giving me opportunity to present my work and ideas. Thank you, audience, for patient listening.
Thank you, sir. I, Dr. Sakshi Paitani, propose vote of thanks to Dr. Sudeep Thepade, sir. Thank you very much, sir, for accepting our invitation. Thank you very much, sir, for sharing your research and experience with us. As nowadays AI in biomedical engineering is being dominant research area, the session will be definitely useful for all of the participants. Thank you, sir.
Thank you, ma'am. Thank you very much.
So participants are requested to stay in the session only. The next session will start within 5 minutes.
With your permission, I'll take leave, ma'am.
Yes, sir. Please.
All
Thank
the
you, sir.
best to all. Thank you.
Dear participants, the next session will start at 11:45 sharp. Thank you. बुलबुले सर. Good morning, Vinayak sir.
Good morning, madam.
Good morning, sir.
Good morning, madam. Are you getting my audio? Yeah, I hope I am audible there. Are you getting my audio, madam?
Yes, yes. Yes, sir.
Okay. Okay.
Good morning, sir.
Good morning, madam.
Sir, with your permission, shall we start?
Yes, we should go ahead.
Hello, everyone. We may now proceed to session 2 for the day. I am Ms. Shraddha Bingardive on behalf of JSPN's Rajarshi Shahu College of Engineering, Department of ENTC. Take this privilege to introduce our speaker, Dr. Vinayak Bharadi, sir. Sir has his PhD in engineering from Mukesh Patel School of Technology, Management and Engineering, Mumbai. Master of Engineering in ENTC from Thadomar Shahani Engineering College, Mumbai. Sir has registered PhD guide in Mumbai University and a registered PhD research supervisor at NMIMS University, Pune. Sir has 17 plus years of teaching experience in various institutes and Sir has about 189 research and technical paper publications and citations. He has a patent filed on a method of retrieving images based on content application based image retrieval from image database. Sir has number of honors and awards. To name a few, Best Employee Award October 2009, received Best Employee Award in Teaching category by Thakur College of Engineering and Technology. Amazon AWS Educate 2019, was designed as a faculty ambassador in 2019 cohort of AWS Educate Cloud Ambassador Program. Best Researcher by VDGOOD in the 11th International Scientist Award on Engineering, Science and Medicine in 2020. Received Amazon AWS grant for teaching Big Data and Analytics Labs in 2016 with INR 5,000. Received NVIDIA GPU grant as NVIDIA Titan X Pascal GPU worth 1.7 lakh for research topic improving performance of Weber local descriptor based feature vector extraction on multimodal biometric system consisting of iris and online handwritten signature. Sir is reviewer to various journals. To list a few, Journal of Real Time Image Processing, Springer, IET Image Processing, IET Electronics Letter, IET, the Journal of Image Processing, and Journal of King's Square University. So we are really fortunate to have you here, and I request you to please start with the session.
Thank you, madam. I hope that I am audible. In between, we will be switching from this presentation to the live Google Collaboratory demo. Again, if you feel any audibility or any visibility issue, then let me know. Maybe the organizers can put it on chat or they can discuss.
Yes.
So yeah, so in this with this preamble and a brief technical introduction, we'll start. So my topic for today's presentation is using long short-term memory networks for COVID-19 impact prediction. So this is the second session. Earlier, so we had a similar session but the participants are having, they are totally new, means the separate set is there. So I will just briefly uh, discuss the idea, because this is the AICT sponsored FDP on AI and its application in biomedical engineering. And this topic that what we are going to discuss today is mainly having the AI and the machine learning and deep learning at its core. And then these deep learning techniques are used for prediction of COVID-19 pandemic number of cases, we will see. And this is the kind of sequence prediction problem using deep learning networks. And where it applies to biomedical engineering is the maybe health conditions and its prediction. Because earlier session I was just briefly there to test maybe the Zoom meeting, and Dr. Sudeep was actually giving a presentation on glaucoma and identification of glaucoma using multi-layer perceptron. So one medical condition was being detected. So it was this is a case where the static data is there. The static means the full image, eye image is there available with you, and then this eye image, this fundus eye image was there, and this you predict what is this condition for that. And uh, other situations are something like that. These are the sequential situations. Means for last 4 days your diabetes reading count is this, or maybe your heartbeat variations are like this thing, or maybe blood pressure variations are. So if you know that this is your past data, past history, means generally when we go to doctor, so they also ask our history, or then for if we are having nowadays this what you can say, this family physician concept is quite fading out, and there are specialists are there, but still the person or the doctor who is visited regularly, this doctor knows her past records, past values of her, what you can say, critical readings. And based on these readings, the person can predict, okay, now this might be your health condition. So similar kind of prediction you can implement with this concept that we are going to discuss today. That is the sequence prediction concept is there. So if you know past data, can we predict the current and obviously future data, not current. So this is the idea. This is the idea. So if you understand the concept, and maybe this again today I am going to discuss this long short term memory network, LSTMs. They are abbreviated. So these LSTMs are also quite means this is a separate type of neural networks, where if you might have heard, this is the special category of recurrent neural networks. So these recurrent neural networks, and specifically these LSTMs, they are very good for sequence predictions. And we have, like, for general, very commonly used example is your Google Assistant is there, Siri is there. So they take your no, speech or commands that, okay, now call my wife, or what is the today's weather, or kind of thing. And this sentence is first of all converted to the sequence of words, and then it is translated, or maybe their meaning is found out of that. So this is where the LSTMs are working at the backend. Not only LSTM, there are lots of techniques, natural language processing and other things are there, but just LSTMs are also there because sequential data is there, and from that we have to predict something. So this is the use. So let us go ahead with the agenda. With this. So today, already now this is AIML DL based techniques that you have studied. So briefly, I will discuss what is AIML DL for preparing the primer. Then RNNs, we are going to discuss in bit depth RNN and long short-term memory network. Briefly, I will discuss the LSTM architecture, because though it is a quite complex thing, not very complex, but it is not a, what you can say, topic which we can discuss in one single lecture of 1 hour. But I will try to make you understand the concept, and then we'll go for a demo where I will show you how to format the data for LSTM. It is not like, it is like even in the past lecture or in any case of neural network problem, we have to process the data. As it is, the neural network cannot handle the data, cannot take the data. If we, for example, fundus image was there in the last, what you can say, presentation, but TSBTC algorithm was applied on that, feature vector was generated, and then this feature vector was given as input for processing or for classification purpose. Similarly, here also we need to process the data. to what you can say, so that LSTM can take it and predict something out of that. So this processing is very important. This processing I will discuss a core concept of how to format the data for this long short-term memory networks, and then we'll have this prediction of this COVID-19 impact cases, just a case study kind of thing, and then we'll conclude. So let us go ahead. So first part is this AI/ML/DL and its brief introduction. So neural networks, actually they come from this neural. It is not a very new concept. Long back in 1956, uh, it was first presented, and then lots of development was there. So there is one main thing is called as universal approximation theorem, okay, on which these neural networks are based. And what it says, or what neural network they do, these networks, they are actually made up of multiple entities. They are called as artificial, these neurons are there, and they can approximate any what you can say complex function. This is the key thing, because when you want to classify something, when you want to predict something, you need to find out the mathematical model of that. So one way of doing this thing is that analyze all the data and fit model to that, and then give input to that model, and you will get the output. Like for example, y equal to x square. This is the model I have. So if I find that some for this function, this is the relation for input and output. Obviously, you give any input, you will get output. But there are some functions which cannot be mathematically modeled, and here neural networks, they come in picture. And that's why, based on this universal approximate theorem, you can build a neural network which will approximate any complex function based on the training data which is given, and then you can predict the data, or you can classify the data. Okay, obviously there will be, now as it is approximate, so there will be, you will have to define what kind of accuracy you will need, and accordingly it will specify. So yes, machine learning is now it has emerged from this neural network. So machines can learn something. So what they do, they actually find the templates and parameters which are best for that template, and based on this template will approximate what you can say the function which the input belongs to. So technically, when we say y equal to x square, it is only two variables are there, x and y. But in real life, there are multi-dimensional. There is a hyperspace, it is called as. So it is not only x, y, but x, y, z, w, and this vector space goes on. So it becomes very difficult to put the function mathematically. Hence, the neural network come handy there. So in case of this hyperspace, this neural network can approximate the functions in a less, what you can say, time and less compute power. And this AI is what you can say, more and less like we are mimicking the way human thinks. So set of rules will be defined, and we can, so neural network and deep learning. This deep learning is actually, we are having neural network with multiple layers, multiple hidden layers. They can just classify. They cannot think on their own. The AI will take this input, will take the set of rules, and then we can say that based on this specific, what you can say, conditions, these decisions can be taken. So this is the framework. So summarizing these things, this AI, ML, and DL hierarchy is that this AI is the superset, machine learning, deep learning, they are the subsets. So AI needs maybe set of rules and programming, but machine learning, deep learning, they can predict, they can classify without being explicitly programmed for the set of rules. So as I said, that they will approximate the function. You have to train the network, but you cannot say that this is the mathematical model for that function. You will have that neural network model. So neural network model, he will have its parameters and what you can say structure, architecture, which can approximate the input data. Deep learning is uh, similar to, not similar, it is a subset of machine learning. But here, because now we are having this that will come in the next slide, here we'll discuss that. So advanced compute architectures are available. We can have now, today also we'll see this thing on Colab. So Colab is giving me higher high-end GPUs and high RAM. So I can go for multiple hidden layers. Even this was actually discussed by Dr. Thepade, where he used up to 200 hidden layers. Okay, that is a very high number of hidden layers that you could use, and it is totally possible. And as compute is there, you could use that. Earlier, this was not the case. So this is a very classic example of deep neural network. So 200 hidden layers were used for classification of certain problems. So here, just a minute. Yeah. So here, what you can see is that on the screen is the interest in deep learning techniques. Now, even I am giving lecture of my PhD was in image processing and computer vision, but now this AI, ML, and DL, this today's deep learning part is a special, or what I can say, very focused what I can application scenario is here when we classify the input data. So there has been clearly two situations where deep learning 1 and deep learning 2. As from 1980s, the solid state devices they are getting interest, they are becoming widely available, and as of late from 2010 onwards, HPC cloud-based systems they have emerged, and they are available at lower cost to the common public. More and more people could what you can say afford this hardware, and you can say that total publications have been increased of late. So there is an exponential growth in the interest of this deep learning and neural networks. So this is a just I discussed this thing. Yeah. So this is regular neural network 1980s era where one single or couple of hidden layers were there. But in case of this deep network, we are having multiple hidden layers. Just a minute. Sorry. Okay. So this is what makes this thing interesting is that because of these multiple hidden layers, these hidden layers can be, this network will learn specific factors of your input data. Here one image is given, like this human image is given, human photograph, but last lecture they gave the fundus image. Now I am going to give the sequential data, that is the sequence of number for a specific no, maybe COVID-19 cases for last 200 days. So based on this thing, this hidden layers, a specific layer can access a specific character of that data, like here ages, then combination of ages, and finally features, and it will predict, it will learn what this input pattern what you can say made up of, and it can predict the thing. So there the idea is that this network will extract feature on its own using this deep learning, what a multiple hidden layers. So you no need to explicitly go for what you can say feature vector extraction. You can directly give the input data, or if you give even the feature vectors which is actually processed by you, the network can perform better if you have more number of hidden layers, and it can classify better. So yes, this is the data availability. We are having this storage and like social networks and many what you can sensors and compute, and in number of issues are there which are making you this data is available to you, as well as they are allowing you to store the data. We are having now petascale data. This neural network and deep learning now we use that thing for weather prediction, insurance, fraud detection, a number of banking and fraud detection. A number of things are there. So it needs a petascale data many times. So this storage and availability is there. Compute resource availabilities are there. Now we'll execute this today's program on Google Colab. So here we will be executing that thing on a TPU, tensor processing units. So they are specific type of hardware which are built to run the neural network. They are built to what you can say process the data which is coming for the deep learning kind of architecture, coming from the deep learning kind of architecture. And obviously because of this data availability and hardware availability, we are having new algorithms are coming in picture. LSTM is one of the example for that. We had this RNN, we had some issue with RNN, and hence these LSTMs are coming in picture. GRUs, gated recurrent units are there. So neural NTUs are there, neural Turing machines. So in number of these new algorithms are there which needs heavy compute, and this compute is available to you. and this has driven the interest in what you can say deep learning. So what this deep learning is doing in these two words are what you can say summarize what we have discussed: correlation and reduction. They will take the input pattern, they will try to find these hidden layers, will try to correlate the data, will remove the unwanted data, and they will keep the data which is relevant, that is the features of this input data, and they will process and predict that. So this we'll discuss briefly the types. No, I'm not going to discuss all the types, but this reference will be required in the what you can say next discussion. So here you can see the perceptrons that we just had. I will take reference, keep on taking reference for this last session because it was a perceptron based, multi-layer perceptron specifically they had used, and in this multi-layer perceptron, multiple levels of hidden layers were there. So this is one type of network which are actually they will take this full data as a whole, and they will process that thing. And then we are having this recurrent neural network. This perceptrons is one class of network, and recurrent networks, where recurrent neural networks will have current as well as past data. They are having time notion associated with them. This is very important part. All the participants who are there part of this session, please make a note of this thing, that this LSTMs, GRUs and RNNs, they have notion of time associated with them. Where in case of this perceptrons, this notion of time is not there. You may have this maybe x and y axis, or maybe multiple what you can say multiple dimensions are there, means multi-dimensional feature vector will be there, but this all features and all data will be given what you can say at one go for training, and it will process that. But here in case of neural network, it will have this multiple dimensions, multiple, and time step notion will be there. This important aspect will what you can say, it will be more clear when we format. Just a minute, sir. लेक्चर गोइंग आहे, लेक्चर चालू आहे म्हणून मी फॅन बंद केला. Okay, so multiple time steps are there, and this we will have to format the data as per for this time step notion. So please keep this thing in mind when we will have the demo. Will what you can say that this concept will be clear. So for today's discussion, our focus will be on this. These are the recurrent neural networks. This LSTMs, GRU, they are a special category of RNNs only. So next we'll discuss this RNN, recurrent neural network. So in case of this simple feed-forward network, that was maybe multi-layer perceptrons, they are very good at learning the patterns. As you can see here, the pattern 8 we want to classify, and we what you can say extract the feature vectors of that, and then individual feature vectors we actually give to our multiple nodes of this neural network. Same thing happened when in the last session when you had this fundus image. Fundus eye image was there, retina image was there, and this one algorithm was applied on that to generate the feature vector 1 array, 2 array, 3 array, or like this thing 10 array, and then multiple hidden layers were taken. So this is actually pattern recognition problem. So they are what you can say learning a pattern between set of input and set of output. So these are, if this pattern comes, this is what you can say glaucoma image. If this pattern comes, this is a non-glaucoma image. But okay, in case of the data which is having sequential of nature, so one very good example here you can see that this is year, you got time, and this is the what you can say specific that may be value of that stock. So you can take this like a stock image. So how this stock has growth. So based on this, you are over the time, and there were various what you can say ups and downs. The stock price has changed. Now, if I have data till this, and I know that this is the history, what is the next value of stock? Okay, will it be here, will it be here, or will it be here? If I'm able to predict that, that can be a gain for me. I can, and this is one instance. There might be weather, because something sometimes it's weather and its conditions we need to, and many weather prediction algorithms and services are there which do use the past data. They correlate on that, they learn that pattern and they predict the next condition. So for such cases where the past data and sequence of, it is not that the data is given all in as it is, rather data and its past value are always important for the prediction of next. This is where the time or train comes, and neural networks of MLP, they will not be used there. Rather, we have to go for the recurrent networks. So recurrent neural networks, they are a special type of networks where what they take, they not only take the current, what you can say, state, but they consider the past hidden state also. Okay, the past state also for prediction of next state. This is technically what you can say, this state comes because of the time, time state part. This is very important concept. The state, in case of this MLB, what you will give, if there are 100 samples, you will give 100 samples or 100 samples with what you can say, with 5 variables. Then you will give everything to that. That will be taken as it is. And in the, all the what you can say time samples have what you can say equal weightage. But here, in case of this recurrent neural network, sample 1, sample 2, sample 3, sample 4, sample 5, they have to given in that sequence, because every sample and its time step has trend associated with it, and that will carry the information for the future prediction. That's why you are having the current input. Here you can say when your current input is there and past input is also there. So current input, past input will generate the next input, and like this thing it will go on predicting. So this is actually unfolding. This is unfolding of this network, and here in summary you are having this input, that is current input and previous hidden. So current input will give this activation function and current output, and this hidden state, it will be forward to the next time step with the next input, so that it will always have idea of what has happened in the past. So current and past state will be used to predict the future states. These are the output states. So this example will take here. So that I will discuss in time. So what happens that this for summary of this slide, important that you should remember or you should take away from this slide is that this network, they will take what you can say input in time steps. This output will depend on current input as well as previous time steps and its impact. So this previous time step and its impact is taken as the previous hidden output. That is the in between output. That's why you can say this is for the first step, there is no previous one, so it will generate the first output, okay, based on this activation function. And this hidden state will be passed to the next layers, because these are next layers. And as you can see now, this one, what you can say, lever only unfolded like this thing. So it will, as time step will progress, this will actually be like this thing. It will keep on giving the current time step to the same network again. So that's why things are recurring, and here's the name recurrent neural networks. Okay, let us go ahead. So here there is one more concept, there is back propagation through time. Generally here in the multi-layer perceptron, we have the concept of back propagation, where the we have this predicted output, then error, and actual output and predicted output, we generate the delta, that is the error. Error, from the differentiation of the error we will generate delta, and it is passed to the hidden state back, so that it will, this weights will be updated and will go for the next, what you can say, pattern. And this cycle will continue until the error is below the desired margin. So that is the back propagation algorithm. What change here, this is again the another key concept of this RNNs, is that back propagation through time. It is called as BPTT. This BPTT. So what happens that it will back propagate through previous steps. So previous steps input will be here. You can see it will generate, it will predict, and it will find out what is the error, and that error will be back propagated through time. Okay, so you accumulate all the losses for each time step, and then we pass the gradient backwards through the network again for training purpose. Okay, so in case of this RNN, we are having the through time step, we are going to pass it back for when the network is getting tuned. Again, this is the complex concept, but just try to remember at least is that in case of multi-layer perceptrons, it is a in case of supervised network, supervised scanning, it is a back propagation algorithm is there where it is difference of error, and it will use for object weights. In case of RNNs, similar concept, but predicted value and desired value, its error, it is accumulated through steps and passed back, okay, again for the updating of the weight purpose. Here you can just we discuss that here for this activation purpose you are having this previous steps. Here you can say it will calculate the current one, and then current output is predicted based on this, and this will keep on continuing. Okay, so here you can see this back propagation through time, or this how these networks are sequentially producing from one step to other. Okay. Just one more thing, they use the tan hyperbolic activation function in case of this RNN. For now, when we want to discuss from RNN to LSTM, this one very important thing that comes in picture. So I understand that these things for these RNNs and LSTMs, they are going a bit fast, but you'll have to cope up with me for this. So what happens in case of this RNNs? Here you can see that this is the time step, while say that t, and rather than here if I say this is a time step t, t minus n time steps are there. And for even prediction of this current time step, what happened and what happened here is important, and that is past. Here you can see for the current time step, this will pass this what you can say ht to the next, and the next and next. So based on this history, I am going to predict the thing. So even whatever has happened with the input and the data and its impact, it is what you can say, it may be important for the prediction which is here, and that should be carried. That should be carried in order to predict the thing. For example, suppose now today is what you can say Monday, and I want to predict some stock price. But some news has happened on Friday that okay, there is suppose a war is there between some countries, and because of that war, today's stock market is going to be what you can say impacted. So it is something like that. So what has happened in the past, I am going to what I can say need that information. Because suppose because of some reason this neural network forgets that okay there was war, it predicts the positive breakout, but because of war there is negative breakout. What will happen? Your prediction is wrong. So this happens because of, or this is important, and that is restricted because of phenomenon called as vanishing gradient problem. What happens that as the network length or as the time step progress, what will happen? This network, these gradients which are important because this outputs or this input of current state, that is past, next state, they become smaller and smaller. This gradient which belong to the time step t minus n, they become so small when they reach the current time step that they hardly impact the prediction. And this phenomena is known as the vanishing gradient problem. This RNN, they suffer with the problem called as vanishing gradient. Okay, so here what you can say, this is the same thing I discussed where during the back propagation vanishing gradient problem. Just a minute. दाते सर लेक्चर चालू आहे माझं. लेक्चर चालू. Okay, so during back propagation of this, during the time, if I am going to time step n, I have to remember previous time step also. And because these gradients pertaining to the past time step, they are very what you can say small, they create very negligible impact. They become so small to actually create impact on the current time step. And this is particularly of very important to us because we are dealing with the recurrent neural network, and time on past time inputs are very important to this. If some key input has occurred in the past, I should be passing that thing to the future. I will give the example for this thing. Here you can see that I want, suppose you want to translate this thing. I live in France and I know dash. So Or let us take in Indian context. So I say that, okay, if I go to USA and I say that I live in India, and I know, what you will say, which language? I know Hindi. But in case of, why you say that I that what is the fill in the blank? If I live in India, I know Hindi, because Hindi is the India's, the what you can say, the main national language. And suppose, as far as context, I live in India. So the moment India is the key step, and I know, if I say language is the context, so India, I should not say French here, I should not say Latin here. India is the most suitable word, sorry, Hindi is the most suitable word here to be predicted. But this fact comes from the, what you can say, instance that I live in India. So this is the content. India, this information that I live in India, that this person belongs to India, should be passed when you want to predict the fill in the blanks where I know. So India will drive the fill in the blanks to Hindi. Otherwise, randomly or maybe past, what I can say, pairwise, it will take the data and you can predict anything. I know English. I know English also. Okay, so this is a problem called as problem of long term dependency, where regular RNNs fail. Regular RNN fails because they just keep on passing the hidden states, and because of that thing, even if important or non-important steps, as the time step will progress, the impact will go on diminishing and diminishing. This is the key problem. I hope that this concept is, I tried to explain that thing, because this is a critical concept, because based on this concept, then these LSTMs are designed. Okay, this is the key concept. See, today even RNNs are also used, LSTMs are also used, but because of the superiority of LLN, these LSTMs, RNNs are almost, they are not used. They are not used. Just for the comparison purpose, we use RNN, because LSTMs are RNN only, but they address this problem of long-term dependency. How? Let us see that. So again, this is quite complex. So what I can say, architecture is there for GRU, but try to I will put the key concept here, and then where the crux is there, that we'll discuss, and then we'll take demo, because demo is important. Architecture, if you are really interested in this LSTMs, definitely you can go through that and explore. So idea is that this long short-term memory networks, they have the constructs called as gates. Okay, they have gates inside them. Okay, so generally we are having this multi-layer perceptron, and one single perceptron will have this summing function with input nodes, and it will give you the output. So, and then these networks will be interconnected, and we treat them in array structure, and we do forward pass, backward pass kind of thing. In case of this LSTMs, one LSTM, there is a notion called as cell. So there will be LSTM cell, and whenever we design a network, we'll always design a network in terms of number of, what you can say, cells in that network. So if I say that there is a layer, and in one layer there are n number of cells, in second layer there is one cell, like this thing, it will go on. So always the layers will have cells. Part of cells will be like this. MLP layers will have nodes. Here this LSTM, deep LSTM networks will have cells, and every cell will have this gate structure. Okay, so forget gate, input gate, output gate. This is the LSTM cell. This is gate number 1, gate number 2, gate number 3. Then this is the current time step input, and this cell always have past time step. So in case of RNS, if you remember, if you see, remember here you can see current input, past hidden state, current output, and then current hidden state. Like this it will go on. So for LHTMC, there is one past hidden state is there, and current hidden state is passed to the next step. This is the RNN. What LSTM gives is this. It will have past hidden state, as well as there is one more entity called as, it will generally called as, one is past output, where you can see it's not hidden state output, it is HT output, and it will have cell state. This hidden state is called as cell state here, and this is very important. This cell state will carry, like I said that I live in India and I know, what you can say, Hindi. This cell state will carry the information which is relevant. This is very important, my friends. Remember this thing. Cell state will always carry the signal or the information which is relevant for the future state. It will always carry. So forget state will decide what to remember, what not to remember. So everything is here is in terms of vectors. The cell state will always will be a vector, and this forget weight will decide what to keep out of this vector and what not to keep out of this vector based on past vector state as well as based on the current input which is going to be there. So that's why this forget gate will take, this is a sigmoid function here. You can say there are two types. Sigmoid function will be squashing the output in 0 and 1, and hyperbolic will be squashing the output will in between -1 and 1. So sigmoid, it will input, it will have input xt, that is the current state input. It be ht -1, that is the past output, and current input will be given. The forget gate, along it will be vector multiplication here, pointwise multiplication here you can say, and it will generate the current cell state for this input gate, and not in between signal, and this what you can say forget gate will keep the relevant thing here. Now this is the relevant part coming to the input gate only. Now again this xt is given to tan hyperbolic fast flashing. Past state is given through a sigmoid. There here vector multiplication is there, and then pointwise addition to generate the new cell, new output state, cell state. Okay, new cell state is here. So it will now, this current cell state will have impact from current input, then past output, as well as relevant part of the previous cell states. So here it will allow this RNN to remember past input which are relevant for future prediction, and they will be carried. This is the very important part. This is the crux where LSTMs they differ from RNN. If you understand this, at least you are understanding the very basic difference between RNNs and LSTMs. Otherwise, these LSTMs are recurrent neural network only, but they are having capacity or design such that they will carry the relevant, impactful inputs to the for the prediction for a significantly longer time. Okay. So if there are certain activities on chat, maybe organizers can know if you have any questions. Okay. Okay, let us go ahead. Yeah, so this I just discussed sigmoid and tan. So this is for this same, what you can say, architecture. This is the here you can see that detailed, and I'm going to share this PPT with all of you. This is a very good slide I got from the internet, where it actually depicts, okay, how this new input event, the previous hidden state, and it is going to be carried where multiplication, where addition, and the new cell state is generated, new output hidden state is generated for the prediction purpose, and then these things will go on concatenating each other. So yes, with this what you can say primer is introduction to this, let us go for this this what you can say, the what is will be our input data, and then we'll have a demo. Okay, so we have still more than half an hour is there. So now idea is that this, with this cell state, with this not cell state, with this LSTM architecture, we are going to build a network. We are going to build a network of this LSTM cells, which will take sequential data as input, sequential data of COVID-19 patients. So what is that? What is that data? Now that we'll discuss now. And based on that sequential data, it is going to predict what will be the next patients. Okay, next patient count, I will say, not person, it will say count. Okay, so if you say, and you may say that, sir, this is quite predictable, it is exponential network, and then you can easily predict. Yes, totally agreed. Here I want to demonstrate how this networks is trained, these LSTMs are trained, and then you can, if you understand this concept, you can use that thing for prediction of any vital parameters. That's what is the situation. Yeah. Yeah, so here this is the COVID-19 data set. So John Hopkins University is there, JHU, You can search it on Google. They are having their Git storage, Git repository, and they update their data every day. I think it is every day twice they update. So every 15 hours they update the data. So it is now this research I did in the month of May, June, July. So I from day zero, that is almost in January, to 175 days, I'm having around 200 days data here. And what data we have is that this global confirmed cases, how many cases are there in all over the world, global deaths, global recovery, then Indian, and how many confirmed cases are in India, deaths are in India, recovery in India, confirmed case in US, death in US, recovery in US. So these are the actually 9 variables are there. You can say this is the multi-dimensional. So multi-dimensional prediction problem is there. So you can take even one single what you can sequence, and here it is multiple sequence. Okay, so this input, so here you can say this is the global confirmed cases, then here global deaths are, this is a red one, so here it is comes somewhere, it is very small, then global recovery is there, then Indian days, and lot this is prediction. You can see that from day 15 onwards, where there we are having the exponential rise in the case. So what I say that I will use this one part of this data for training, and I will train the network till here, and let us see whether this network can predict data, which is next COVID impact. So here this part, can the network predict? Let us see. For implementation purpose, we'll be having Keras framework. So Keras is the library. Actually, it is a high-level API which is programmed in Python, and it is using TensorFlow also, TensorFlow functions. So actually, we are having Python library, Python programming framework. Over that TensorFlow is there, and over that Keras. So Keras is what we are going to use this Keras functions to build the LSTM networks. Okay, so we are having less what you can say customizability here, but high level abstraction is there, and with small number of lines you can build a what you can say sufficient network which can predict the cases. So here I will spend next 15 to 20 minutes to make you understand what is this concept of time step, and when we go for this preparation of this network. So when we prepare any network in Keras, there are 5 stages that we have to go for. Maybe in any other language also. You have to define the network, compile network, then fit the network for this, then train the network, then prediction, we evaluate the network for training data, testing data, and then based on that we can always predict predict the output based on whatever the time step or inputs what are there, classify. So let us go for the demonstration. So I will now present my screen once again. I hope that you are getting this my browser on the screen. Okay, if organizers, if you are not getting, please let me know.
Yes, sir.
Okay, okay,
Yes, sir, it is visible.
fine, very good. Thank you, madam. So this is Google Collaboratory. For those who know, it is okay. But what those you don't know, I will just briefly explain what is this. This is a online cloud-based uh, virtual machine actually, which is given to you. You will need Google account here, and using that thing collab.google.com, collab.google.com. You can write Python code here. You can write, you can use TensorFlow, you can use Keras, this library by installing them, and directly, because TensorFlow and Keras, they are natively available with Google Colab. You can directly use them for the, so those who have used Python and those who have used Jupyter notebooks for Python programming, this is the same thing. It's exactly same. Only thing is that you don't need to install anything. I don't have Python installed my native PC. Whatever this laptop you can see screen is shared, there is no Python compiler installed. Everything what I am doing, it is totally cloud based. And here you can see that the configuration for the machine here. So if you it might not be legible to you, but now I am having this 12 GB RAM and 100 GB storage space which is available to me, and runtime here you can say. So runtime is there. I'm having this by default. TPU is there. I'm not changing any runtime because it needs restart of that machine. So tensor processing unit TPUs are there on which this program will be run. Okay. So and these programs will be by default stored in your Google Drive. Even these programs you can fetch data from Google Drive. So even though you don't need to store anything on your local machine. So full it is totally cloud-based demonstration is there. Yeah. So see, we are not going to discuss line by line what is the thing, what is the situation. Idea is that first I will show you the key steps to create environment, define the network. So here you can see define the network. So there is something called a sequential model. Sequential model means for the layers which will go one after the other. One after the other we are going to add the layer. So here we can, this is simple. I will this code, critical code I am going to share with you. Just try to understand what I am speaking. If you have any problem, we'll have this question answer session. So idea is that first I am defining a neural network model which will have this LSTM cells. So here I am going to define one network with single layer of LSTM, 10 input cells and one single output. So 10 cells are there. Input shape as of now you will discuss later. That is the way it is going to take the input. Okay, input data, sequence data and output. So these are the next step when we prepare the network. Here this is the important part that we'll discuss. We'll put some more time on that. Then directly go for the final work model. So this is a function which will generate the data. Here you can see that I am going to generate the first sequence of number, 60 numbers. I am this here you can see this generated, and this is a sequence creating data. So idea is that this is the input sequence and it is a shifted one. You can see the one step it is shifted. So if 0 is current input, next step will be 00295. 295 next step is this. So if I'm having 080984, network should predict 090269. Now what is the next value based on the past one? This is the idea. The current step, next step. So this is just understanding purpose. We are going to discuss this thing again. So here X values and Y values we are generating from this sequence. So in case of Y, this Y step, this is second column I'm going to take as Y. This first column I'm going to take as X. So here I am going to define the network. That is the first thing, and it is the summary. So this network has got two hidden layers and sorry, not two, three hidden layers. Here you can see three hidden layers and one output layer. Okay, so here this network summary is there. Next step is we just discussed first define the model, compile the model. So it is like compiling the program whether this network model is properly designed or not. Optimizer, if you for your information, when the network is designed, there is something called as the optimization, means the error is there, and there is something called stochastic gradient descent. Gradient descent algorithms are used to minimize the error and find the optimum plane where there is a least error. So for that purpose, the way we move the error, various optimizers are there. So SGD, ADAMS, things are there. So here we are using the ADAM optimizer. And mean square error, what should be the method how we calculate the error. So MSC I'm going to predicted value, actual value, MSC we calculate, we find the optimizer and we'll update the weight and it will continue. So here this is the next thing, that is the fitting the network. Okay, where input then output, that is desired output, and we are going to train the network. So this is the training for that last 60 inputs. It is going to train itself. Last step is the evaluation part for training data, testing data, and here it is the finally predicting the values. Now it is the prediction of all 60 values. That let it be, we'll just what you can say, discuss that later on. Here we'll come back and I will discuss this very important concept, which is their key part. Now this, those who are interested or maybe uh, they find that okay, I can use that thing, this thing for my research, and you want to continue with this thing. This is very critical thing. If you understand this thing in today's discussion, you can use this LSTM for any kind of future problem. So try to understand this concept as far as possible, because it is very difficult. There are very less number of books, majority articles are there online, and from that I learned and I experimented and I got this concept. It is there available on the net also, but difficult to understand. So once you understand this thing, you can formulate the problem. So let us start. So idea is that, see, I said that neural network of LSTM type, they will take data in case of sequential data is there. So this is the general term. Okay, I'll say that layman's term, that sequential data will be given. But technical, that you want to program it here. So what is the same? What is the change? How to do this thing? You understand this thing. So network will always take data which will have the format of sample, time step and features. Remember this thing, or maybe you can note, or if I am going to share this thing, I am going to download this thing right now. Yeah, and then maybe after this I will upload the file after this discussion. Okay, so I will upload 2 files for your discussion. So I will explain this, give this thing to you also. So you can directly run this thing in your Google Colab. You can upload to your Google Drive, open your Google Colab, this will run. So let now understand, always you will have to format or reformat or reshape your sequential data as sample, time step and features. So what is the sample, time step and feature? I'm going to put time here. So this features means what? Your number of variables. So if I say that will come, and we are going to link this sample, time step, feature for our COVID data, don't worry. So that's why this term will come again there, but that's why you will have to install, remember this thing now. So sample means what? How many individual data sample points are there with you? How many individual data sample points are with you? So here I will take example of stock market prediction for all of your, what you can say, understanding purpose, because it is better understandable there. So I say that today is now suppose 15 December and I am having this last year data, means from January to December I am having data. So every month I will have maximum of Sensex value for every month. So what I will have how many samples? I will have 12 samples for last with this month also till date I will have maximum value. So from January to December I will have 12 Sensex value which were the maximum per month maximum. Fine. So how many samples are there? 12 samples are there, and I want to predict the January Sensex value. Okay. Now this is one thing, sample. Okay. Now I say that's feature. So I say that now adding one more step here. I say that okay, I have Sensex value, but I will take Indian GDP value also and Nifty value also. So when I am taking sample, I will have BSE Sensex, Nifty and GDP as well. You can say that okay, I will have inflation rate also. So Sensex, Nifty, GDP and GDP prediction you can say, and inflation rate. So 1, 2, 3, 4. So in every sample that I take, this four values I am going to take as input for last 12 months. So I am having now 12 samples, and every sample is having how many variables? 4 variable, that is the Sensex, Nifty, GDP and inflation rate. So they will be features. So 4 features are there: Sensex, Nifty, GDP and inflation. So 12 samples and how many features? 4 features. So hope that now you got this sample and feature idea. Time step is very important. That's why we'll discuss that later. We stood right now only. If you understand sample, if you understand feature, now let us discuss the time step part also. Now I say that in order to better predict the movement of Sensex, rather than having only monthly, I'll say that I will have weekly reading also. So I am going to now expand this data briefly. By adding for every month the weekly maximum of Sensex and these values. weekly maximum Sensex and these values. Okay, or you can say that weekly closing. So every Saturday's value I will say, Friday's value. So there are, I will consider every month 4 week. Okay, at least it will have 4 weeks. So from starting from last week onwards. So for January we'll have 4 readings, February 4 readings, March 4 readings, like this thing. So every month we are having, instead of initial one sample, we will have final this four values. Okay, so for every month we'll have 1 2 3 4 4 weeks value, 1 2 3 4 4 weeks value. So and every week's value will have Sensex, Nifty, GDP and inflation. So 4 readings were there for last 12 month, 4 4 4 4 12 into what you can say 4 week, 48, and every sample has got 4 variables. So number of samples are 12. Number of features are 4: Sensex, Nifty, GDP, and inflation. And number of time steps are 4 weeks. That is the week 1, week 2, week 3, week 4. So 12 sample with 4 time step and 4 feature vector. This is the understanding. If I am going to repeat it one more time, but briefly, this is the concept of sample, time step, and feature. Whatever may be the LSTM, even you want to go for your biomedical implementation, you will always have to give the data in this format. So if you say that I want to give a person's blood pressure, now we'll take different example: blood pressure, then heartbeat, then blood sugar, and maybe what I can say, diabetes level. So blood pressure, heartbeat, blood sugar. Okay, diabetes level, blood sugar, same. So I will take three pair. I am not medical expert. So blood pressure, heart rate, diabetes level. These three will be the feature, and I will take the person's this reading of every week. That is the week 1, week 2, week 3, week 4. These will be time step, and same thing I will repeat for 12 months. So these will be samples. So for 12 months, I am having every week reading of this blood pressure, heart rate, and maybe the sugar level for this person. So 4 time step, 3 variables, and 12 samples for last 12 months. So this way the data has to be given to the LSTM. So if you understand this concept, then maybe you can again start. There are many online examples are available, and you will understand the prediction process. Now again come back, we'll come here, and we'll try to gather the thing for this prediction, today's prediction purpose. So here this is the briefly what you can say, relating the same thing. So here whatever this model that we are what here, this is a simpler explanation for that. Here what I am going to do is that here that we consider this thing initially, that this is the sequence, input sequence 0 0.1 0.2 0.3 0.4 0.5 up till 0.9. There are 10 samples are there, and 10 sample, every sample has got one single reading. So that's why you can say input shape here, input shape, one time step and one feature, and it is single variable. It is the simplest what you can say LSTM prediction problem, simplest LSTM, one single variable, one time step, and 10 samples. So with this I have designed this input. Here you can see this LSTM is designed here, 10 cells. Okay, there will be 10 cells will be there. You can take 100 also. It is not that because of 10 sample I am designing. Here I will design with 100. Okay, here you can see it has predicted. Here you can see. So these are the actual values and these are the predicted values. Okay, we will find that 0, 0 0.01, 0.1, here something like next value it is predicting actually. So you can say 1, this next shifted value. So for 0 it is 0.1, for 0.1 it is 0.2, for 0.3 it is 0.4, something like that it will go on predicting. So idea is that here you can see this for 10 samples, one time step and one feature, this network is designed. I want only one value output. That's why here final output is dense and only single prediction. And with this, the network is defined. Here network is compiled with Adam Optimizer and MSC, fit with X and Y. Here you can say now is X and Y are here from this value only that we defined above, and prediction on the x. That is the input. That is, here you can see again this input, when it is given, it is reshaped. That's why here you can say, rather than only giving as sequence, it is reshaped as 1 and 1. So I will just, for your information, I will just put this shape of x. Here you can say 9 1 1, and we'll just predict, we'll just display x, what is actually sample, time step, and feature. Here you can see now this is actually a multi-dimensional array. Actual input is like this sequential input, but it is reformatted. It is formatted as 9 samples. It is formatted 9 samples, and every sample is having one time step and only one feature. So 9 sample, one time step, one feature. This is the input. This is the input which is given to this input, what you can say as. So actual, for our layman, it is sequence is this, but when it is given to this LSTM, it is reformatted as this sample, time step, feature. So this is the crux of discussion. So if you discuss this, if you understand this thing, you can correlate this to any sequence prediction problem. Okay, so with this primer, now let us go ahead for yeah, I will just briefly, now I will not run because this actual program is to be demonstrated. So this is example of no, I will just show you. Yeah, two series, two variables. I just, you can say series one. Oh, I hope this is visible to all of you because screen is shared. Now earlier we had only one sequence, but now this is the example of data formation for two sequence, series 1 and series 2. So here now 10 samples are there and 10 comma 2, here you can say 10 time steps you can say, and two variables are there. Okay, so in order to actually, this is the 10 samples. In order to put it in what I can say LSTM regime, so I will say that here one way of putting this thing is that one single time step having one single sample having 10 time step with two variable. So this is reshaped. Here you can see 1 10 2 new series dot reshape. So this is single sample, one sample, 10 time step, 10 time step, and two columns. That's why two variable. So that's why here this LSTM is trained at 10 time step and two, what you can say, input, two variables, two input, two variables. So this is the input shape of multidimensional series. Okay, this is the next. Okay, here also. And let us go for now today's this problem of LSTM prediction. Yeah, yeah. So here COVID-19 prediction problem. So with this now all this formation and input. So here I am having this collab only. So what I am having here is that these two commands, I am actually fetching data from my Google Drive. So this one input sequence I will just plot. This compile USB was there. It is already there in my, I will just run that. I will show you on my Google Drive. Compile, yeah. Yeah. So just I will be switching the screens. Are you getting the screen? Yeah, this Excel is displayed here. You can see. So on this Excel, total recovered global, total recovered India. So total deaths India. So this is the actual. This is a value. This is Excel. I am going to use this thing for training. Total 117 entries, 116 entries are there. Okay. So this data I am giving as input. This data I am giving as input to this. So actually it is on my local PC, but sync to Google Drive. So here it is read into a data frame and plot for your reference. So here you can see this is the input sequence. Now this input sequence is taken into a data frame. So it is read into data frame. So total global recover, total confirm India. Here you can see total death. Now from this, sir, from this data frame, now what sample time step features, remember this thing, sample time step feature. Still this is our input data only. So how, what is the size of this input data? Okay, I will show you data frame. What is the size of this input data? 116 and 19, sorry 9, 116 9, 116 rows and 9 columns are there. So we have to now, this is only input data, but we have to format as now what is the current state, what is the next state, and then sample time step features. So that formatting we'll have to do next. So these are the functions which are, so here it is, I will be using. So what actually I am doing here is that, next step is that from this data frame 116 19, all this variable they are shifted one step, they are shifted in one step, so that it will be training that okay, this is the current step, so next step is this, the current step training data, next step is this, current step, next step is this. So I am giving that okay, if you get this input, next step in the past was this, if this is the, this was the step, next step in the past was this. So I have to shift it by one cell. You can vary that thing also here, there for that functions are there, in out. So here you can see that t minus 1 var, and here var t. So if t minus 1 is there, what is the var t? So till here up to 9, this is the upper data that we had, and this is the shifted data. So for training purpose, so now the shape of this thing is 115 comma 18. So 18 columns are there. First 9 are input x, next 9 are y. Whatever series you want to predict, the next step is here for training purpose. Okay, here you can see. So from this thing, we actually separate the what we want to predict. So I'll say that first two variable I can predict 9 also, but for understanding purpose, I'm taking 2. So these two features, first two, that is the first two variables. Let us see that total global recovered and total confirm India. For example, these two variables we are taking for prediction purpose. So if I am giving this 9 variable as input, it will predict the next thing. Still, this is the x and y I am separating, that is the input and outcome, input and outcome I am separating. Okay, then this is training and testing data separation. So 92 inputs I am going to take for training, 92 sample for training, 23 sample for testing. Here comes the very important part. Here, that is the choose the number of time step we want to see. We have to now reshape how many time step will be there. So we till this part we are having 115 sample and 9 variable, 115 sample and 2 variable. For for input 115 sample and 9 variables are there. For output 115 sample and 2 variables are there. This is quite what you can say natural, because we are having the sequential data 120 samples and the tabular data is there now. But this LSTM needs sample time step features, sample time step feature. So every sample must have to be received in this thing. Every sample must be defined with time step. Okay, so what technically I'm going to do is here is that I'm going to reformat this table such a way that I will separate every sample so that it will actually have its next sample with it. So technically it will have, rather than 115, it will have around 230, and every single sampling instance will have data of 2 days, 2 time step I am taking. Okay, so every single time instance will have. So technically I am having collecting data like this thing. If data pairs like this, today's data, yesterday data, today's data, yesterday data, today's data, yesterday, like such, like this thing I am doing for 115 days. So sample and time step. So again here you can see I can specify number of steps here, number of steps too, and it is going to reshape that thing, split sequence. Actually, it is now reshape function is modified to split sequence. So 90 samples, 2 time step and 9 variables. So initially we had 92, but now the sampling will take one variable from this 19 as now addition purpose. Hence it will reduce the overall samples by 2. So instead of 92 by 9, we are having now input data as 92 samples and 9 variables. We have 90 samples. Each sample is having 2 time step and 9 variable. Output will be same. And so at a time when I give the input, I will give a sample as 2 time step, 2 days data, and it will predict what will be the next day's data, like this thing. So it is actually, I am going to add local information. If I am going to say today, so I am going to pass yesterday's data also. So predict tomorrow's data. So this is very important. 90 sample, 2 time step. Similarly, I will do for testing data. So this is now our data is ready. Our data which is to be given to the LSTM is ready. Next thing is to define the LSTM. So here you can see now number of steps, number of features. Okay, so n steps, I will run this thing here. So number of samples are 90, number of steps here 92 are 2, number of features are 9, and number of outputs are 2. Here you can see 2 outputs are there, two variables in the output. So this number of output and number of features are 9. So this input shape will have time step and features. So 2 time step and 9 feature, 2 time step, 9 feature. Output layer will have number of output equal to this 2 output I want to predict. So it will always predict 2 output, and it is having what you can say 2 hidden layer, 1 input layer. Here, this is input layer. This is the in between layer. You can say so. This output of this thing will be this layer will be passed to this layer. Then again I am adding one more hidden layer, and so 2 hidden layer, 1 input layer, 1 output layer. This is the LSTM network. Here you can see that this is the input layer, hidden layer, output layer. So input layer, hidden layer, output layer, dense. Here this actually this represent the LSTM and dense, because output of LSTM is encompassing the dense layer. That's why here you can see add layer dense. To this output which are coming from this layer, so they are given to dense to combine 2 outputs. So technically this is the network that we have built. So let us train the network. We can briefly time. See, in like this MLP, for this network, these graphs are irrelevant. I will just say this accuracy, because it is predicting. They might be, what I can say, not as smooth as. So this is the training and addition loss for this. We have to actually impose this data on the prediction. So let us first predict this thing. Testing. What will not predict? XT. Test data. So 2 variations are there. Let us see how much time I have. This I have predicted. I will just put it on actual graph. Here it is on actual graph. Network predicting. Here you can see. Now what you can see here is that here this is the actual path or actual data which was moving, and network has predicted like this for this global confirmed cases, and for this global what you can say global death, this is the thing. So this network is what you can say somewhat following the trend. Now to better what you can say predict the network, there was one stateful implementation was there. Let us I will briefly run that thing rather than explaining, because some other time we can explore, because there are stateful and stately LSTMs are there. What happens that in LSTM there is a concept called as state management. So when one cycle of this training data is complete, the internal state is reset. Now whether to reset after the batch of every 5, that batch size is also there while we train that thing, or whether to reset after every iteration, and that is actually state management of LSTM. And if we better manage the states, we have better output. That is the idea. So same thing I am repeating, but state management is introduced, and because of that thing, the prediction is improved. That just I want to show. Everything is same that we did. This is a network, and only one simple layer is there. Here you can see batch size. Now it is introduced here, and this is the state managed. So it will now run, and this reset is done after every iteration rather than automatic management of states. And because of that thing, network learns better, and we are having better predictions. Yes, now the network is trained. Let us predict. This is not the prediction. Let us superimpose on our actual data. Here it is that. Here now, as compared to previous one, this is having a better actually alignment with the output. So our network now here idea is that now based on this 82 days data, we are now predicting for next data. An actual count is here, predicted count is here based on the past. So here we have used this LSTMs for the prediction of our COVID-19 cases. So I stop here. We'll have some, this 1 o'clock is already there. We are having this session for question answer. I'm going to put this code file here, just 2 samples. I will just, so 1 code file I am putting here for those who can code file in the chat. Second one is also there. You can see those who are interested, they can download and explore. Okay. Then presentation also I am putting. Okay. Then the data which is there required to train the network is also there. So it is open to you. Those who are interested, they can explore. It is there on chat. Yes, thank you for your patient listening. If you have any questions, I'm there. Yes, organizer or any participant, if they have any question, let me know.
Hello. Yes, sir. This
Yes,
is Dr. Paithane, madam.
yes, madam. Yes, madam. Go ahead.
So can we proceed for the question, sir?
Yes, yes, we can proceed.
Could you please share the resource for COVID data?
I have already shared, madam.
Is
It is
it
on chat. This compiled uv.csv, it is the file which is taken for the training, and that is shared. We can see that I have shared 1, 2, 3, 4 files. 2 are the code files, and 1 is PPT, and 1 is the data set.
okay? Okay, sir. Thank you, sir. So if you are there, can we use LSTM only for time series? That question is again repeated. So
LSTM only for time series. LSTMs are designed for time series prediction only, and they are, that's why there is notion of time. See, now those is if you have attended the previous session and this current session. So in the previous session we had this fundus image and given to MLP. So there was no notion of time or sequence kind of input was not there. You had maybe 100 or 1000 MLP these fundus images and then classify, recognize the pattern in one class. Now here difference is that I am having the 115 days data for this 9 variable, and based on that I have designed the network in such a way that I will going to predict the next value. Okay, so I took the 82 days or whatever 92 days data and then predicted next 23 days data or 8 days data based on that. So then that was marked with the red color. Okay, so it is a sequence prediction. This is possible, and RNNs are there. Then you can use GRUs, gated recurrent units, that is what you can say modified RNNs only. So these two things are totally possible for sequence prediction. These are the things which they use, or RNNs, recurrent neural networks, for translation purpose, like English to French translation, English to Marathi translation. They use RNNs and LSTMs only. Yes. Any other?
Yes, sir. Thank you, sir. So with this, we are at the end of question answer session.
Okay.
So thank you, sir. I, Dr. Sakshi Paitane, take this opportunity to propose vote of thanks to Dr. Vinayak, sir. Thank you very much, sir, for accepting the invitation. The session was very interesting with valuable takeaway about the LSTM. Thank you very much, sir.
Okay, madam. Thank you. Good day.
Good day, sir. So participants, the next session will start at 2 o'clock. Please do join. Okay, thank you.
डायरेक्ट से बंद कर देगा। विलॅप करतो विलॅप नाही
thing is, if we are going to allow some misclassification, right, we are going to towards soft margin classifiers. Right? So I would like to, I mean, have a journey from hard margin classifiers to soft margin classifiers. Right? I think is this topic, as you know, this topic is, I mean, you all of you must have heard of this SVM classifiers. How many of you have heard of and used SVM classifiers? Participants, you can say yes, you can type yes in the chat box. Yeah, so just to have a feedback. Chat, okay. So thing is, how many, you can type in the chat box and let me know how many of you have heard SVM classifiers, right? And then how many of you have used SVM classifiers? Can you type in the chat box, in the group chat to everyone? Are you attentive? Yes. Aruna Paute is saying yes, sir. Yeah. Anybody else? Now this is yes to request, or you have used SVM classifier. Are you aware of SVM classification, SVM classifier? Ganesh Gaikwad is saying no. Okay. Right. So these are two representative, I mean, replies. Anyone else? The thing is, this is the drawback of this online kind of session, right? You need to wait for, I mean, the responses, and the participants might not be really ready to respond, right? But I'm saying you can type in chat box, right? So thing is, okay. So what I mean, assume from these two replies that, I mean, almost 50% of you, I mean, I have got two responses. One response says yes, other says no. So almost 50% of, I mean, you know SVM and must have used SVM classifier. Now, thing is, with this background and with this, I mean, thing, let us move ahead. And thing is, this SVM classifier, the treatment of SVM classifier, right? The things which are available, right, are bit mathematical, are a bit analytical, are a bit somehow a bit complex, right? I'm not going to somehow creating a fear of SVM classifier in your mind, right? But the thing is, this is a bit analytical, bit mathematical, and then you need to be very, very patient to understand this, right? I mean, if you look at the, I mean, slide, this tail side, the like below portion, right? The footer as such, right? You can see that number of slides are 22. So number of slides are very less, right? But all the slides are heavy in mathematics, right? The thing is, I will be going at very, very slow rate so that you can understand something about it, right? The intention out here is not to make you fully understand this topic, but the intention is what kind of things are there, right? How to approach those things and how we can get familiar with this, right? And then how we can use this SVM classifier very, very effectively in our applications is the attempt, right? So is it clear? Once again, you can type in chat blocks. Yeah. Participants, are you awake after lunch? And you might have, I mean, light lunch, right? Because you are at home. It is not traditional FDP lunch. Participants, some feedback? The intention, what I really wanted to do out here, is it clear? Yeah. No, nobody's responding. Yes. Aruna Pauti is awake. Yeah. Okay. Other participants, I don't know whether they are there in the front, in the front of screen or somewhere else. Right? I really don't know. Right? Okay. So with this, I mean, background, let us move ahead. Let us go to next slide. And the next slide deals with, next slide, this is the outline, right? We are going to understand, I mean, what is a linear classifier. Then we are going to understand the beginning into SVM classification, right? what SVM classifier, right, the hard margin and soft margin classifier really do, right? To understand this, we need to understand perceptron learning algorithm, right? And perceptron learning algorithm used to classify the data points which are available, right? And then we are going to move into SVM formulation, which is based on the underlying principle is finding out optimal separating hyperplane, right? The thing is, SVM classifier is going to give us the optimal separating hyperplane, right? So we shall understand what is it, what is optimal, when to call this as optimal, and so on. And then I don't know whether the time will permit or not. Then we shall learn something about SVM for linearly non-separable classes, right? And then we will have SVM kernels, right? So this is the flow, and let us go through this step by step and understand the details. Okay. Okay. So in the beginning, let us understand what do we really mean by a linearly separable data and a non-separable data, right? You can see two figures on your screen, right? The figure on the left, this figure, right? You can see that, these squares, this is, what is the data out here? What is the dimension of X? The dimension of X, this X belongs to what? X belongs to R2, right? So what is R2? X is a vector containing two elements, and both the elements are having real values, right? So X is like this, right? So this is might be, let me zoom out a little bit so that entire slide is available. To 15. Page height. Yeah. Okay. So this is the data which is available. So let's assume that this axis is x1 axis. Axes are not drawn. So this axis is x1 axis out here, right? And this axis is x2 axis, right? And we have a vector x, right, which is of the nature x1 and x2. It's a two-dimensional vector, right? And there are several such points available here, right? A few points are shown by red square, right? And a few points are shown by purple circle, right? And a boundary is shown over here, right? Nothing is, if the points are like this, right? And if it is possible to draw a line, because this is a plane, right? This is a two-dimensional space, right? The thing is, a hyperplane in this scenario happens to be a line, right? So if I can draw a line, right, and if I can separate the available data points into two partitions, right, such data that is available with me is referred as linearly separable data. So this is this linearly separable data, right? As against this, like look in this right hand side figure, right, wherein once again the type of the nature or the number of points, x happens to be belonging to still R2, right? So x belongs to R2, right? But the points are like this, and it is not possible to draw a line. So if I try to draw a line over here, right, like this or like this or whatever, right, you can see that a few, like purple points, assume that this is a straight line, right? So few purple points are like on the left hand side of this line, and few points are here, right? Same is the cases, few these blue points, blue squares are left hand side of this line, and few are on the right hand side. So it is not possible to draw a line and separate these 2 points or these group of points, right? Such data is called as linearly non-separable data. So this is linearly, this right hand side, this is linearly non-separable data, right? And as against this is linearly separable data, right? And we want to in the beginning understand a linear classifier, right? So linear classifier will, you must have understood this. We'll go to next slide and we shall understand what is a linear classifier. right? So we will be discussing this linear classifier, right, wherein this linear classifier are going to achieve a linear boundary between classes, right? So if the boundary is linear, then I mean linear classifiers have a role. A linear classification always achieve a linear boundary between classes, right? So thing is, this is the way. Then only, I mean, that kind of classification is termed as linear classification, and those classifiers are linear classifiers, right? Linear classifiers are going to achieve a linear boundary between classes, right? So I mean, in the previous, I mean, figure, there were two classes. There can be k number of classes, and we can achieve a linear boundary between these adjoining classes, right? So thing is, I mean, there are many ways. So we are going to discuss in the beginning linear classification and even hard margin and soft margin linear classification, right? And then we will be moving on to, I mean, this kernel trick, which is going to achieve a non-linear classification, right? So thing is, there are many approaches, right, for linear classifiers. The first and I mean, like simplest approach is using discriminant functions, right? So is it possible to find out this? Let's say there are k number of classes, right? So is it possible to find out k number of I running from 1 to k minus 1? So is it possible to find out these discriminant functions, right? And whatever unknown variable, unknown data point, I'm going to apply these discriminant functions on these, I mean, unknown data, which I want to classify in amongst k classifiers, right? So thing is, if I'm going to apply this, right, how the classification is going to proceed. Now remember that this is to be learned. All these discriminant functions are to be learned. So if I, let's assume that we have learned this, right? So how the classification can be achieved? We can apply, we can get this unknown data point with us. We can apply discriminant function, all the discriminant functions on this unknown data, and the one wherein we get maximum, right, of this maximum value of this discriminant function argmax. So the moment that classifier or that discriminant function for which we get maximum, that would be the class of that data point. So this is how classification would proceed if I'm going to use discriminant function based classification, right? And this discriminant function can be achieved by using linear regression, right, or by using logistic regression, or by using technique like LDA. These are a few methods, right, via which it is possible to obtain these discriminant functions, and then I can apply these discriminant functions on the unknown data, and then we can proceed with classification, right? Thing is, these discriminant functions, I mean, one comment is written out here, right? And that comment is these discriminant functions themselves could be non-linear, right? Like in, for example, logistic regression, the discriminant functions are non-linear, but the boundary between classes happens to be linear, right? So the discriminant functions themselves are non-linear. We can apply some transformation on these discriminant functions to get the linear boundary. Like in logistic regression, the function is a logit function. So we can apply a logit function on these discriminant functions to get the linear boundary, right? So the point out here is the linear classifiers are going to achieve a linear boundary, and the linear classification can be done, can be achieved by using discriminant functions, and it is possible to learn the discriminant functions by using linear regression, or by using logistic regression, or by using linear discriminant analysis, right? So these techniques are going to give us discriminant functions, and we can use it for classification, right? The thing is, I assume that you know some of these things, and we'll proceed. And the topic that we are going to discuss today is directly modeling a hyperplane, right? So as I mean said, this is a hyperplane. This is a line in case of two-dimensional data, right? A hyperplane happens to be a line in case of two-dimensional data, right? So in case of three-dimensional data, it's a plane, right? And in case of four and onwards dimensional data, it is a hyperplane, right? So is it possible to come up with, I mean, modeling of hyperplane means come up with these coefficients like W's and V's, right? So can I come up with directly, can I come up with these I mean parameters, right, which is going to represent hyperplane, right? That is what is meant by modeling a hyperplane, right? So we are going to understand, right, how can we model hyperplane directly. right? And there are a couple of techniques, that I know, right? Which is the first technique is this perceptron model based technique to model a this hyperplane, and the another one is SVM based technique, which is going to model the hyperplane, right? So let us understand very quickly, right, the perceptron model, so that will be base, or that will be motivation to understand something that is better than this perceptron model, which is a optimal separating hyperplane, right? Am I audible, participants? I'll get my water bottle. You can type in chat box. You can type in chat box and let me know your feedback. Am I audible? The host also can tell us. Host are away. Host are moved out. Participants, am I audible?
Yes, sir. Yes, sir. Clearly audible.
Okay. Okay. And is this a pace fine, or am I going at very slow rate?
Yes, sir. It is okay, sir.
It is okay, no? Okay.
Yes, sir.
I'm not in a hurry to complete everything, right? Whatever time that is given to me, I really wanted to deliver something, some conceptual thing that you can understand, and then you can carry ahead, go ahead with those things. And whatever literature or whatever papers that you will go through, that you will read, be it would be a little bit easier when you go through such papers, right? Okay, so let us move ahead and let us understand.
Yes, sir.
Yeah, let us understand perceptron based model for coming up with hyperplane, which is going to give us hyperplane, right? So this is a perceptron learning algorithm, right? Now, like prior to that, what is a perceptron? What is a perceptron? Are you aware of this? You can type in chat box. What is the perceptron, Aruna? Now, for the benefit of all, right, I will draw the perceptron here, right? One type of neural network, right? Okay, 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 okay. The basic type of neural network. True, right? I will briefly explain what is a perceptron, and then we shall understand this perceptron learning algorithm. And if you can see over here, right? The thing is, if you can see, most of the slides are like this, having a lot of math, right? So thing is, that's why I'm going to go at very slow rate, and so that you can understand something based on this, right? And I appeal to the participant that whatever we discuss out here, right? You have a notebook with you and try to note it down, try to write it, right? So that you understand something over there, right? So thing is, this perceptron is a kind of neuron. So let's say this is a neuron, right? Let's assume that this perceptron has got p number of inputs, right? So inputs are from x1 to xp, right? Now these inputs over here can take any real value, right? So x1 can take any real value, right? X2 can take any real value, right? And so on, right? Now there is one more input, right? Whose input is one, and the coefficient. The way the connections, right? Or these lines which are shown from which the perceptron is going to gather inputs, right? Are having weights. So this weight is beta 0. Let's say this weight is beta 1. This weight is beta 2. This weight is beta p, right? So there are p plus 1 weights, right? And then this perceptron, right, is going to aggregate these weighted inputs, right? So what is that? This is going to aggregate these weighted inputs, and then if this is like greater than or equal to 0, the output is like a step function, right? So if this, whatever this aggregation over here, if it is less than 0, we are going to get 0, and if it is greater than or equal to 0, let's say we get 1, right? So this is the perceptron. This is the way the perceptron is going to operate or function, right? So this, I mean, I'll write expression over here, the summation I running from 0 to p, right? Beta I, right? xi, right? If it is greater than or equal to 0, right, we are going to get output y. Let's say this output is y, right? So we are going to get output y1, right? If it is less than 0, we are going to get output y0, right? So this is how like perceptron is going to function, right? Where we assume that this x0 over here is 1, right? So x0, this is x0, which is 1, right? I hope that you know this, right? This is just for revision, and then we are going to use such perceptron, right? This perceptron, right, to like I mean achieve classification, right? So once again, the thing is we are going to find out, we are this perceptron learning algorithm is going to give us these values of betas, beta 0, beta 1, and beta 2 in this case, right? So once again, data in 2 dimension is shown over here, and then for 2-dimensional data we are going to get 3 if this x, input x belongs to R2, we are going to get 3 coefficients, beta 0, beta 1, beta 2, right? So thing is, in general, if x belongs to Rp, right, we are going to get p plus 1 coefficients, right? So this perceptron learning algorithm is going to give us p plus 1 coefficients. Condition 2, what is the condition? If these data points over here, the data points, you can see the marker, I mean this pointer, right, mouse pointer, you can see the mouse pointer. Hello, can you see mouse pointer? A very small dot. Swati, Shraddha, Amruta. Hello, Swati. Hello, Amruta. Hello. You can speak, right? I mean,
Hello, sir. Can you please repeat the question, sir?
Can you see this little tiny dot, which is a mouse pointer? A tiny dot here on the screen. This tiny dot. Hello. Hello.
Hello. Haan, sir.
Can you see this tiny dot?
Not actually, sir.
Mouse pointer. This
Yes,
I am
yes,
writing.
yes, sir. Yes,
Where I
sir.
am
Yes, sir.
writing this very tiny dot.
Yes, sir. Yes, sir.
Okay.
It is visible. Yes,
Yes,
sir.
yes. Okay. So every time I need not, I mean, encircle and this do whatever, right? So you can see this tiny dot, right?
Yes, sir.
Okay. So thing is, I mean, this as we were speaking, right? Thing is, this perceptron learning algorithm, this perceptron model we just discussed. So this perceptron learning algorithm, right, will be successful in modeling, in generating this hyperplane, right? Modeling or generating hyperplane is nothing but revealing or getting the values. I mean, estimating these values beta 0, beta 1, and beta 2. It is successful in achieving this hyperplane if these data points which are given to us are linearly separable, right? So if, I mean, the data point themselves are linearly separable, right, like this, clustered like this, clustered like this, right, then it is possible to, I mean, this whatever algorithm that we are going to discuss is going to converge, and then is going to give us values beta 0, beta 1, and beta 2, right? So to understand this, right, let's, this whatever line that is shown here, this line L which is shown here, right, equation of this line is beta 0, just I spoke, beta 0, beta 1, right, and beta 2 multiplied by xi1, xi2, right? And this hyperplane, right, this line, right, now if there is a point xi, if there is this point xi, on this hyperplane, let's say this is the point xi, right? So if there's a point xi on the hyperplane or on this line, in case of this two-dimensional plane or two-dimensional space, then this equation is going to give us value 0, right? So this beta 0 into beta 1 xi1 plus beta 2 xi2 equal to 0, right? If this xi, if this point xi belongs to line or is on the line, right? So very simple to understand, right? Now thing is, now if this for any other point x now, right? For any other point x, now if f of x, right? Now remember that this is our f of x, right? So if f of x is greater than 0, right, then we will get this gx, right, as x, which are shown in the screen, right? So all these points, right, if I like, I mean, whatever the, I mean, x1 and x2 coefficients or coordinates of these points, if I put these coordinates in this equation, I'm bound to get this f of x greater than 0, right? And for these points, for green points which are shown, if I put insert coordinates of these points in the same equation, this f of xi, we are going to get this value less than 0, right? So thing is, we are going to achieve, or this perceptron algorithm is going to give us this equation of line, right, which is going to do this, right? And then we can find out distance, right? The moment we get this, we can find out distance of the given point from the line, right? And from this distance, remember that distance in this case is a signed distance, right? The moment we have a hyperplane or a line over here, right, the distance we can, for unknown point, we can find out distance, and if that distance is greater than 0, we can classify that point as belonging to, let's say, red region or crosses, right? And if the distance is less than 0, that point is classified as green O points, right? Or I can say that if I denote these class as -1 and +1, right? So this belong to class -1, right? And this belong to class +1, right? So thing is,
माझं चालू आहे सध्या, तुमचं नाही घेणार. माझा व्हॉट्सअप शेअर आहे त्याला. तुमच्या आहे ना, इथून हे सेटिंग मध्ये जा.
Yajuvendra, yeah, can you mute? Yeah. Okay. Okay. So let us understand. Let's assume that this beta, right? Beta is this vector beta 1, beta 2. What is missing? This beta 0 is not there in this vector beta, right? So let's assume that we have vector beta, which is, I mean, collection of these two elements, beta 1, beta 2, which are these parameters, right, in this hyperplane, right? So these parameters, beta 1 and beta 2, right, let us understand very quickly some properties, right? So that, I mean, that would be very useful in understanding at least hard margin classifier, right? So that, let's assume that we have x1 and x2 points, 2 points belonging to line, right? Then this property is true, beta transpose into x1 minus x2. Now here x1 and x2 are 2 points, right? X1 is a point belong to R2, right, and is on the line L, right? X2 is a point which is R2 point and which is on the line L, on this hyperplane L or on this line L, right? Now if I put these 2 points in this equation and if I subtract, right, I get this. If I write these two equations, if I put this x1 in this equation, I'm going to get 0, right? If I put x2 in this equation, I'm going to get 0. And if I subtract, right, we are going to get this property beta transpose, right, where beta happens to be this beta, right? So beta transpose x1 minus x2 is going to be 0 in this case, right? So it's a very important property that we have to understand. And the second property is, if we have x0 belonging to line, right, some point x0 which is on this line, some point x0 on this line, right, then beta transpose x0 is equal to minus beta. Once again, if I put this x0 in this equation, we are going to get this, right? And those who, I mean, cannot, I mean, digest this beta transpose x0, for them I'll write what is beta transpose x0. Beta transpose is what? Beta 1, beta 2, right? Because this is transpose, this has become now row vector. And what is x0? We have first element of x0 and second element of x0. So we have x01 and x02, right? So what is beta transpose x0? Beta 1 into x01 plus beta 2 into x02, right, is equal to minus beta 0, right? So if I put this x0 in this equation, we are going to get beta. I'll now rub this, right? So beta transpose into x0 is equal to minus beta 0, right? Once again, by going to this property. And now next very important property is this beta star transpose, right? So what is beta star transpose, right? Beta star transpose is, this beta star is, I mean, beta by norm of beta, right? So beta by norm of beta is, let's say, beta star, right? So beta star is beta by beta. So what is beta star? Beta star is a, beta star is unit dimension or unit length vector, right, in some direction, right? So norm of beta is 1, norm of beta star is 1, right? So norm of beta star is 1. This, I'm sorry, this is not the point. So norm of beta star is 1, right? So it's a unit length vector, right? So this beta star, this transpose should not be there. So beta transpose, beta star is, let's say, this unit one dimension, a unit length vector, right, in dimension, in direction beta, right? So beta star transpose into x minus x0, where x is any unknown point, where x is any unknown point, right? Now this is equal to, what is beta star? Beta upon norm of beta, right? Now this two lines and beta is norm of beta, right? Norm of beta is length of beta vector, where beta is a vector, right? So this, I mean, if I decompose this into beta by beta norm, right, and if I multiply by beta inside, what do we get is beta transpose, like, I mean, x, right, into beta transpose into x0. What is beta transpose into x0? Minus beta 0, right? So that minus and minus, this minus and this minus will come, I mean, become positive. So what do we get is, we get this expression, right? So beta transpose x plus beta naught, right? Now this is what, this is our f of x, right? So this is our f of x, right? And this norm of beta, right, is nothing but, I mean, this norm of f dash of x, right, where f dash of x is the gradient of this, I mean, x, gradient of f of x, right? So this f dash of x is gradient with respect to x, right, of f of x, right? So f of x by norm of f dash x, this is referred, very important thing to understand, this is referred, this is very important to understand even SVM classifier, right? So thing is, this, I mean, f of x by norm of f dash x is referred as sign distance of a point x from point x0, right? So this is referred as sign distance. And let's say if we select beta as having unit norm, right, now this denominator will go away, right? Denominator will become 1, right? So thing is, if I multiply, if I simply take any point x and put in this equation, we are going to get f of x, right? Now this f of x will be positive, right, if x is lying above this line, and this f of x will be negative if the point lies below this line, right? And then we can use this information to classify, right? You can use this signed distance, right, to classify, right? So these are very important properties, right, with this, with respect to this diagram and the hyperplane, that one has to understand, right? Any query over here? Any question? Shall we move ahead?
Yes, sir.
Okay. Okay. So now the perceptron learning algorithm, right? Perceptron learning algorithm specified on this slide, right? Nothing is, I mean, we can just, now we have said that we can, this is what f of xi, right, where xi is inserted in this equation of line, right? Now, when can we say that the point gets misclassified? Right, the point gets misclassified if the class of the point is 1 and we get this value less than 0. Right, if this is the case, right, we say that the misclassification happened. Right, other scenario is if the class of xi, if the data point, the class of that xi is -1 and we get this value to be positive, greater than 0. Right, in that case we can say that misclassification has happened. Right, now when this will happen, when these values of betas are not proper, not correctly estimated, right, or when training is going on, right, or right in the beginning, right, if we do not know that equation of line, we are bound to get these things, we are bound to get misclassification. Right, and thing is, I mean, iteration by iteration, this perceptron learning algorithm is an iterative algorithm to find out values of beta 0 and betas. Right, and the moment we find out beta 0 and betas, we get entire information about hyperplane, and then we can use hyperplane to classify. Right, so these are two scenarios which are very, very important. Right, and somehow the perceptron learning algorithm, right, should reduce this distance. Right, so the underlying principle of learning algorithm is minimize distance. Right, so this is a distance, just now we have said the sign distance. Right, so we are going to minimize distance of misclassified points to the decision boundary. This is the underlying principle. Right, underlying principle is minimize this distance of misclassified points to the decision boundary. Right, so thing is, now this distance, right, this is the distance. Right, and if I multiply by yi, if I multiply by yi over here, what will be the value? This yi or gi over here. I mean, there is this instead of this is yi. Right, this is yi. Right, so if we multiply by yi, this value would be, this multiplication would be negative. Right, if this yi is negative and this is positive, this multiplication is also negative. And if I negate this, this quantity would be positive. Right, so this quantity would be positive. Right, now thing is, we are going to, underlying principle is minimize distance of misclassified points. So thing is, this is the set, these xi's and yi's are the set which belongs to M, where M is set of misclassified points. Right, so I'm collecting distances of all misclassified points, a positive quantity. I'm collecting distances of all misclassified points, and I'm going to minimize this, is the perceptron learning algorithm. Right, so this d, which is the distance, right, this is as if an objective function now, and we are going to minimize this. Right, what are the parameters which are available with us so that we can minimize this distance? Right, b and beta naught. So we can adjust b and beta naught systematically, right, so that the distance is minimized. And ideally, what do we want? If the boundary, if there is a linear boundary that can exist, ideally we want this to be 0. Right, that is, there is no misclassification. Right, moment there is no misclassification, M is an empty set. Right, and if the M is empty set, there is no argument over here, the value would be 0. Right, so at that time we can say that our algorithm has converged. Right, and we got an hyperplane. Right, so how this can be done, how we can adjust these values systematically? We can adjust these values systematically by using a very famous algorithm. Right, that famous algorithm is gradient descent algorithm. Right, now where the gradient descent algorithm says that obtain the gradient of this, I mean, loss function. Here loss is minimum distance of misclassified points. Right, so we can obtain the, I mean, partial derivatives, right, of this distance. We can differentiate this function with respect to betas and beta naughts. Right, moment we differentiate with respect to beta, this is, I mean, beta is a vector over here. Right, so we get this gradient of d with respect to beta. Right, so beta is, what do we get? Beta is, we get minus yi xi, the summation. I mean, the, I can take differentiation operator inside, and if I differentiate, especially this is a vector and this is a vector. Right, if I differentiate this, we get xi. Right, and differentiation with respect to beta is 0 over here, so minus yi xi. So dou d by dou beta is summation I belongs to all these points which are misclassified minus of yi xi, where yi is actual label, xi is the point, right? Similarly, this partial derivative of d with respect to beta naught is minus yi, right? So I can take with respect to beta naught, for with respect to beta naught, this is constant, right? And the time derivative of beta naught with respect to itself is 1, right? So thing is, so this is 1 and this is 0, so it is only minus yi, right? So dou d by dou beta naught is minus yi, right? So these are, I mean, derivatives of this distance with respect to beta and beta naught. And gradient descent algorithm says what? I mean, subtract, I mean, move in direction opposite to gradient, right? So thing is, if we move, let's say if this k, and k is the current value, and if I want to update the value, right? What is the updation rule in case of gradient descent? You subtract this gradient from current values. You scale this, I mean, gradient, scale by rho, right? And subtract this from current values to update the values, right? So this is the update rule, right? So if I subtract, I mean, this become this minus, and this minus would become like positive. In general, this is plus, so beta k. So value of beta at kth iteration, value of beta naught at kth iteration is equal to yi xi and yi, right? Scaled by rho, right? This is my value at next iteration, and then I can continue iterations till what? Till this m becomes empty, right? And there are proofs available in literature which shows that this algorithm really converges if data points are linearly separable, right? So this is very simple perceptron learning algorithm, right? And this is going to learn the values of beta and beta naughts. Let's move ahead, right? So thing is, in case of perceptron learning algorithm, rho equal to 1 is suitable, right? So thing is, this row over here is 1 in case of perceptron learning algorithm, right? In case of, in general gradient descent algorithms, this learning coefficient, right, is very, very small. But in case of perceptron learning algorithm, right, this row 1 is suitable, right? And if data is linearly separable, then the learning algorithm will surely converge to some solution, right? Nothing is the obtained solution. However, now the problem with this perceptron learning algorithm, the obtained solution is not unique, right? And depends on starting point, right? And the sequence of points handled in the iteration, right? So the moment, the way we handle these points, right, the hyperplane is going to change, right? And there could be many solutions which are available, right? One more drawback of this perceptron learning algorithm is it takes very long time to, I mean, find out this hyperplane, right? Especially that is true when separation between classes is very small, right? And if the data is not linearly separable, then the algorithm doesn't converge. Algorithm keeps on going on, right? So thing is, I mean, I would like to show you that, I mean, over here, let's rub this first. Right? So think this is one hyperplane that is shown, right? It is possible to have a hyperplane like this, right? Or like this, or like this. There are many solutions which are available, right? That is what is said as the solution is not unique, right? It really depends upon starting point. What are my starting values of beta 0 and beta vector, right? What are these values? So depending upon these values, one might get a different hyperplane. So solution is not unique, right? This algorithm is slow, right? And especially slow when two classes are very close. If the points are very close out here, these points are very close, it takes very long time to converge, right? So these are the problems with perceptron learning algorithm, right? And the perceptron learning algorithm is going to work only when data is linearly separable, right? So thing is, with this understanding of perceptron learning algorithm, let us move ahead, right? And let us understand this SVM formulation, or what is the underlying principle of SVM, right? And how do we get, and what is the optimal separating hyperplane? Okay. So thing is, once again, consider this scenario. Look at this figure. Am I audible?
Yes, sir.
Okay. Okay. So consider this figure, and let's understand that these are the 2 points. These are two, classes of data points and number of points over here, right, shown by purple color and this blue color. Right. Nothing is the perceptron learning algorithm might give us this plane, such kind of planes. Right. What is optimal over here? The optimal, model that one can get. The optimal model that one can get is whatever shown in the figure, right? So ideally what do we want is, we want a hyperplane like this, right? And we want a hyperplane having maximum separation, right? Having maximum separation like this, right? Ideally we want a hyperplane like this, right? Which can separate data, linearly separable data like this, right? Having maximum separation between these classes, right? So we want, ideally we want plane like this, right? And we want bounding or boundary planes like this, right? So thing is, now we are going to understand how can we achieve this? How can we achieve optimal separating hyperplane? Right? So optimal separating hyperplane is that plane which gives us maximum separation. Right? And once again, if you apply all the properties, right, of these, whatever property that we discussed, right? Nothing else. This, let's assume that this, distance, this distance between two, these bounding planes or boundary planes is m, right? So thing is, the underlying principle of support vector machine classifier is maximize this distance m, right, of closest point to the hyperplane. These are points which are closest. This is the hyperplane that we get. You want to maximize this distance, right? So adjust this hyperplane such that distance is maximized, right? So this is the underlying principle or objective function in case of support vector machine, right? The thing is, we want to maximize this m, right, by adjusting beta and beta knots, right, such that this, norm of beta is 1. Not this norm of beta, there is, remember that, this m is function of beta, right? So we cannot have any arbitrary large value of beta and then maximize this, right? So with norm of vector beta 1, we want to maximize this m, right? And remember that if equation of this line, right, equation of this line is xi transpose beta beta naught equal to 0, right? So the convention out here is, this w is nothing but beta over here, that's it, right? And beta naught is b, right? So equation, the this line is just whatever we discussed is xi transpose beta plus beta naught equal to 0, right? So what do we want is, we want that this, this, if I multiply, right, by yi, right, if the point is on this side, this is going to give me, this negative value. The point is on this positive side, going to give me positive value. So this yi, if I multiply by yi, this quantity is always positive. This quantity is always positive. Just a minute. This quantity is always positive, right? So thing is, we want to maximize m such that this multiplication, the sign distance, right, is greater than or equal to m, right? And for I running from 1 to n, so for where this n is number of points, right, for all points, right, we want that the separation is maximized, right? That is the underlying principle and the objective function in case of support vector machine, right? Now we can get rid of this norm equal to 1 constraint. Remember that now this is constraint optimization. And remember that in case of support vector machine, right, we need to understand, right, some terminologies from optimization theory. So those who want to really understand this, right, should understand some terminology from optimization theory, right? The thing is, we want to optimize or maximize this margin m, right, by these are parameters. These are optimization parameters. We can optimize, we can change these values systematically, right, or somehow, right, under constraints. Constraints are norm of beta is equal to 1, right, and these are n number of constraints. So total there are n+1 constraints, right? So constraint optimization problem, right? And support vector machine is going to solve constraint optimization problem, right? Now we can get rid of this norm of beta equal to 1, right? By going by inserting this, by putting this value, we can get rid of this by the following, where in this constraint, right, we can put norm of beta, beta by norm of beta, right? So this beta is a regular beta, right? We can make norm of beta equal to 1, right, by having beta by beta norm multiplying by 1 by norm of beta, and then we can ignore this because we already considered while considering this condition or this constraint, right? So thing is, y into this 1 upon norm beta xi transpose beta plus beta naught is greater than equal to m, right? Now remember that I can take this norm of beta outside, right? So if I get this norm of beta outside and if I rescale beta naught, right, if I want to get this 1 upon norm of beta outside, I should be in a position to multiply by norm of beta over here, right? Then only I can take outside, right? So that if the moment I go inside, it will cancel and the equation doesn't change, right? So thing is, I can rescale beta naught appropriately. So even though from moving from this equation to this equation, this beta naught and this beta naught, the label used the same. This is a rescaled beta naught, right? And I'm keeping the label same, right? So rescaled beta naught and the, but the label is same, right? So the thing is, I can have this constraint, right? So I can, write this equation like this by suitably rescaling beta naught. And thing is, moving ahead, right, I can take this 1 upon norm of beta naught on the right hand side. So this equation becomes like this, or the constraint become like this. And then by setting, right, norm of beta naught equal to 1 by m, right, this right hand side will become 1, right? So all the constraints now, right, can be rewritten like this, right? So this is yi into xi transpose beta plus beta naught must be greater than or equal to 1, right? Thing is, these are all constraints and these are constraints for all n data points, right? So we want to maximize now. What is the the objective function rewritten? We want to maximize now m. It was m, right? It was m, but m is equal to 1 upon norm of beta, right? So actually this is 1 upon m is 1 upon norm of beta, right? So we want to maximize m. So maximize this. So maximizing this is nothing but minimizing. Now remember that, just see earlier slide, it was maximize the margin, right? Now it is minimize, right? Minimizing this norm beta, right? Minimizing norm beta is nothing but maximizing margin, right? And there's a little change in the objective function. Instead of minimizing norm beta, we minimize norm beta square, and then there is one scaling factor which doesn't change formulation, right? Nothing is, this is with an purpose so that our this optimization becomes convex optimization problem, right? So this is the final optimization problem that we are going to solve, right? Wherein we are going to minimize half norm of beta square subject to all these constraints, where yi into xi transpose beta plus beta naught greater than or equal to 1 for all the points where n is n number of data points, right? This optimization problem, this formulation is very, very important to understand, right? Once we understand this, we can move ahead and we can understand what is the solution of this, right? We will speak for 15 minutes ahead and we'll try to understand this is hard margin classifier. Thing is, wherein we understand that the data points which are given are linearly separable. So if the data points are linearly separable, there is no misclassification. We cannot tolerate any misclassification, and we want to find out a equation of hyperplane which is going to maximize the margin, right? Okay, so thing is, this some terminology from optimization theory, right? And I will narrate this, right, over here, so that, and then you can go back, refer back, and refer the notions or concepts from optimization theory, and you can understand more, right? So thing is, whenever there's a constrained optimization problem, we can find out Lagrangian, right? So this is the Lagrangian which has been formed, right? Wherein, this was, the margin, this is representing the margin, and these are all constraints, right? And you can see that these constraints are greater than or equal to 1, right? In case of, while solving this, we want constraints to be less than or equal to, right? So this has become 1 minus this. So this becomes 1 minus this, less than or equal to, right? I can take this on the right hand side. I can write down 1 minus into bracket yi xi transpose beta plus beta naught less than or equal to 0, right? So these are the constraints, right? So we need to rewrite these constraints, these inequality constraints. These are referred as inequality constraints, right? So we need to write down or rewrite these inequality constraints in terms of less than or equal to 0. After rewriting, what can be done is we can have these Lagrange coefficients, alpha i's, right? And we can form a Lagrangian, right? So this is a Lagrangian which has been formed. This sign is minus, right? So because this is written as this term minus 1. Had it been 1 minus, this would be plus, right? Which doesn't cause any difficulty or problem, right? So this is the Lagrangian, and this problem they call as a primal problem, right? So this is primal, right? It's a primal problem. So thing is, in case of optimization theory, there is a dual problem. So we can convert this primal problem into dual problem. Remember, that's a convex programming problem, right? So this is a convex programming problem, and we can convert this into dual programming problem, wherein, this was maximization, right? This was minimization, right? So now the dual problem is maximization. Can convert this primal problem into dual problem, right? So there is, way to convert this primal problem into dual problem, wherein we write this Lagrange polynomial as it is. You can see that it's written as it is, right? So maximization is maximization, right? Now the parameters have changed. We can maximize with respect to alpha all these Lagrange coefficients, right? Now condition have changed, right? What are the conditions? Nothing is this gradient with respect to beta and beta naught, which were optimization variables in case of like primal. What are the optimization variable? Beta and beta naught, right? So the thing is, these are the optimization problems. By, you can see that in the dual problem, now the optimization variables are changed, right? Now I can fine tune alpha s such that I can maximize this, right? So this is primal problem, dual problem is like this, right? And minimum value of this is maximum value of dual, right? So dual problem is a concave problem, right? And we can certainly maximize. So we can maximize this Lagrange polynomial, whatever this, functions that is available over here, by changing these, Lagrange coefficients. One important condition have appeared over here. And that important condition is this point, right? This Lagrange polynomial, the betas, right? We should select those betas for which Lagrange polynomial, gradient of Lagrange polynomial with respect to the optimization variables of primal should be 0, right? So this should be 0, right? And then one more constraint, which is alpha I, right? Alpha I should, all these Lagrange coefficients should be greater than or equal to 0 for all the points, right? So this is not there. So this gradient should be 0. Gradient of this Lagrangian should be 0. The like whatever Lagrangian that is available in the primal problem, right, should be 0. So this turns out to be, we can, if I achieve solution of this, it achieves solution of primal problem, right? So the thing is, why to go to dual, and why to understand, why to solve this, we will understand, right, if time permits, right? Otherwise you can go and really, go through the literature and understand, right? The thing is, it is going to lead to some simplification, right? And remember that if we have, and there is one theorem, if we have this convex programming problem, right? The thing is this, I mean, dual is always concave, right? And I mean, if there is, I mean, there is a strict duality, then I mean, this minimum of this primal is equal to maximum of dual, right? So there is a lot of theory behind this. I mean, whatever the conversion and transformation, which one has to understand, right? So thing is, to understand support vector machine, right, you should understand how to solve constrained optimization problem using in the form of primal problem and the form of dual problem, right? Once you understand this, right, how to solve this, right, how to have formulation and how to solve this, things becomes very simple, right? And remember that, I mean, at least, I mean, why am I focusing on this? At least we need to understand these forms, right? And we need to understand one more terminology so that things are very simple. And the terminology is these, I mean, solving dual problems, right? Nothing is this gradient with respect to beta, this LP is the moment we take gradient with respect to beta of this LP, what we are going to get? We are going to get beta minus summation I running from 1 to n alpha I yi xi. How are we going to get this? I will explain for only, I mean, first equation by referring back the previous slide, right? Right. Now thing is, this is, we want gradient of this. We want gradient of this with respect to beta, right? So what is gradient of this? Twice beta, right? This can be written, beta norm square can be written as beta transpose beta, right? So gradient of this is 2 beta, right? And this 2 and 2 will cancel, right? So this would be beta, right? Then if I take gradient operator inside, and there's only one term over here which involves beta. So, and that term is alpha I, yi, and then xi, right? So thing is, I mean, this can be written as beta transpose xi, and I can take gradient with respect to beta. Then what do we get? Alpha I, yi, xi, right? Gradient of beta, gradient of this LP with respect to beta of this beta naught is 0, is constant, right? So thing is, what we are going to get is beta minus this summation is there, I running from 1 to n alpha yi xi, right? So this is what is written here, right? So this is the gradient of LP with respect to beta, right? So beta is equal to, I can take this, I mean, on the right hand side, beta is equal to this, right? Similarly, I can take gradient, right, of LP with respect to beta naught, we will get this condition, right? And the, I mean, dual optimization problem can be restated because these are the conditions, right? The gradient of, I mean, LP with respect to beta and beta naught should be 0, right? So by putting these results in the primal problem, I can have a modified dual optimization problem, right? So this is a modified dual optimization problem, right? Wherein now, I mean, the objective function becomes summation I running from 1 to n alpha I, right? Half summation I running from 1 to n summation k running from 1 to n alpha I, alpha k, yi, yk, xi transpose xk, right? So simply, I mean, these results which are obtained here, these results which are obtained here, if we can insert, if we insert this in this expression, and especially in this expression, right? If I insert value of beta over here, beta transpose beta, right? If I insert value of beta, what we obtain, beta not what we obtain, and if we simplify, right, we will get this expression. Right? Okay. Any question based on this?
Yes, sir. Not actually received any question from the participant side.
Okay, okay. I shall continue for 10 more minutes, right? So that we can understand this. right? Now remember that, I mean, look at this form, right? Now this form is very, very important form. This dual optimization form is very, very important form. Where you just concentrate on this. How can we train this? How we, I mean, there is inner product of x and x happening. Where what is x and xk? Inner product, right? What is x and
थोडा
xk?
आवाज कमी करते बाबा रागवत होते काय करून हल्ली म्हणजे ते टीव्ही जवळ
हॅलो
Yeah.
वानखडे मॅडम हॅलो
Wankhede
वानखडे
madam.
मॅडम
Yeah. Okay.
प्लीज म्यूट युअरसेल्फ
Yeah.
सॉरी सर
No, it's okay. Okay. So this, you can see this form in case of dual optimization problem. You can see this form, how xi is appearing in this expression, right? There is this inner product where what is xi and yi? These are data points, right? So inner product of data points is happening in this expression, right? Now this is very important from SVM kernel's point of view, which will come later on, right? So this is the dual optimization problem is maximization by having these optimization parameters alpha I. I can change, I mean, these alpha i's such that this gets maximized, and the only condition now is alpha I greater than 0, and this one more condition over here, alpha I yi should be equal to 0, right? Nothing is, we can achieve, we can find out solution, and there is a role played by these KKT conditions, right? One more notion that you have to understand, right? While solving constrained optimization problem is these KKT conditions, right? Now these KKT conditions are necessary conditions to tell you that we have the solution which achieves, I mean, minimum, right? These are necessary conditions, they are not sufficient conditions. In case of convex programming problem, right, the KKT conditions are necessary and sufficient conditions, right? So once these conditions are satisfied, we can say that we have achieved solution, right? So what are KKT conditions? Right. Now, KKT conditions, I mean, this dual problem can be solved either analytically or by using algorithm like sequential minimal optimization, SMO, which is based upon chunking, right? Which we will understand little bit later, right? Nothing is, what are KKT conditions? KKT conditions are, these are KKT conditions. These, whatever written over here are KKT conditions. The first condition is stationarity, right? Remember that we have inserted those values of beta and beta naught for which gradient of LP is equal to 0, right? Then the second set of conditions is primal feasibility, where this is the primal feasibility conditions, right? Wherein we want that this distance multiplied by yi should be greater than or equal to 1, right? And then dual feasibility, which is alpha is the Lagrangian coefficient should be greater than 0 for I running from 1 to n, where n are number of data points. And the last KKT condition is complementary slackness, right? Very important condition, right? What it says, this alpha I multiplied by this constraint should be equal to 0. So either this should be 0 or alpha I should be 0, for which this has to satisfy, right? So if this is not 0, alpha I should be 0, right? If alpha is non-zero, this should be 0, right? So that this complementary slackness condition is satisfied, right? So if these four conditions, if those are satisfied, we have achieved our solution. So we can have any analytical solution, or we can select any algorithm like sequential minimal optimization, and we can solve this optimization problem, right? Now we can say that, I mean, thing is, here we can use computer tool, right? What is important to understand in case of this hard margin classifier is what is the role played by this optimization. I mean, what is, how this formulation has come, right? And what are KKT conditions? These are KKT conditions, right? And then we need to interpret these KKT conditions, right? So let us understand these KKT conditions, right? Now, case number one, what is case number one? There exists this point, this is there exists where this is greater than 1, right? Now, what are these points where distance is greater than 1? Those are far away from hyperplane, right? So for the points which are far away from hyperplane, for those points, alpha I, which are Lagrange coefficients, could be 0. So this corresponds to all the data points beyond the margin, right? And second important condition with like by considering complementary slackness is where this is equal to 1, right? Now when this is equal to 1, Lagrange coefficients are greater than 0, right? So the moment we get solution over here, moment we get solution of this optimization problem, we are going to get values of alpha i's, and from these alpha i's we can immediately find out that which are the points which are away from this hyperplane and which are the points which are on the hyperplane, right? So thing is, whenever this is equal to 1 means this is 0, right? So alpha I should be 1 in that case. So this corresponds to all the data points lying on the boundary of margin, right? So these xi's are referred as free support vectors, right? So these xi's are referred as free support vectors, right? And once we compute beta, right? Betas are computed by once we have optimal solution of dual. So once we get alpha star, right, and this condition is true, right, it is possible to compute betas, right? Now how do we compute betas? Betas can be computed by using this, right? So thing is, the dual optimization problem, once we solve, we get alpha i's, right? We know y and xi, right? So there'll be some points for which alpha i's would be non-zero. For most of the points, alpha i's could be 0. So thing is, those points, right, for which alpha I are non-zero, these are support vectors, right? So this beta, right, which is going to give us, I mean, the hyperplane, right? That hyperplane can be obtained simply by linear combination of support vectors, right? So this is simple linear combination of support vectors, right, from which I can obtain beta, and then once we obtain beta, we can compute beta naught, right, from all support vector points and taking average. Remember that, I mean, we can have this condition, right, for which, I mean, we have computed beta and we have got this condition, right, and we know x and yi, right? So thing is, those points for which are support vectors, from that we can compute betas and then we can take its average, right? So moment we take it average, we have got everything. We have our betas and beta naught, and we got our hyperplane, and then we can simply, I mean, plug in the value of whatever point that we want to classify, right? We can plug in into this estimated hyperplane. We can take the sign, and based upon sign, we can go for classification, right? So thing is, and this can be done is, I mean, how do we put this here? So this is x transpose beta hat, right, plus beta naught hat, right, where beta is what? Alpha I, yi, xi, right? And this is unknown value, x is unknown, right? So I can compute this, right? And I can add beta naught, and I can find out this f hat of x, from which I can immediately conclude whether the point belong to class 1 or class 0 by knowing sign of this. Remember, that's a sign distance. So by knowing sign of this, we can immediately conclude that whether the point belongs to class 1 or class -1, right? Any question based on this? Right? So the thing is, I mean, we will, I mean, just, I mean, initiate what is soft margin classifier, and then I will stop. Now remember that, I mean, whenever the, I mean, data points which are given are not linearly separable, right, which has been shown in this figure over here, right, and some non-linear boundaries shown over here, right? Remember that hard margin classifier cannot achieve the result, right? So we have to now relax condition, right? So by relaxing condition, now we can allow some misclassification happening, right? Remember that this is the misclassification that has happened. This is the misclassification that has happened, right? All these solid points are on, I mean, top half of this hyperplane. All these hollow points are on the bottom half of this hyperplane, right? Nothing is, we can allow misclassification to happen, and then we can go for what is called as soft margin SVM classifier, right? So wherein, I mean, I will just tell this optimization, I mean, what is misclassification and how is it manifested? Nothing else. Remember, in, I mean, earlier case, yi xi transpose beta naught, E was greater than or equal to m. Now we relax. We relax this condition by adding these xyides, right? So now we have this we allow this misclassification to happen, right? Where all these xi's are greater than 0 and summation of xi's, right? For all the values, we have some constraint, let's say some maximum value, maximum tolerable misclassification, right? So by relaxing this condition like this, we can have a soft margin misclassifier, soft margin classifier, and then we can go ahead with this, right? So I mean, I will urge to participant to understand all these theory, right? And I mean all the optimization theory, right? The primal problem, the dual problem, and the KKT conditions. Once we understand this, and once we understand all these equations of hyperplane, the notion of sign distance, right? It is very easy to put down, right? The problem, understand the problem. Remember that we are going to use computer tool to solve, but to have a formulation, right? And to, let's say, have a value to decide upon values of this constant or some other constants in SVM, we need to understand this theory. Once we understand this theory, we can put appropriate parameters and we can achieve the desired classification by using SVM classifier. So that is the takeaway point, the message that I want to give. Yeah. So I will stop at this point and I can take a few questions if there are any. Yes, Swati. Swati.
Hello.
Yeah, I am ready.
Yes, sir.
I can stop at this point and I can take a few questions if there are any.
So the one question that I have related with the deep learning actually. So for AI, the data set is very large. So this linear classifier are not reliable. Is it true, sir?
Nothing is this. I mean, there is something called as SVM kernel, right? You can, I mean, I have not gone ahead, right? So where you can have this SVM kernel and you can have really a non-linear boundary, right? You can have this kernel trick, right? You can have this kernel trick, SVM kernels, right? Wherein you can transform the given data into higher dimensions, right? And you linearly classify the given data in higher dimensions, and then you project back, get the boundary in original dimensions, right? Which would be non-linear in that case, right? So this SVM kernel trick, right, allows us to transform the given data into higher dimensions, do linear classification in higher dimensions. Remember, for example, if we have this RBF kernel, right, the dimensions are infinite, right? So we can have such kernel and then we can go for linear classification in higher dimensions. And once we come back to original dimension, the boundary becomes non-linear, right? And then we can achieve whatever desired classification. It is possible to achieve classification like this if we desire. It is possible to achieve classification like this if we desire, by converting this data into higher dimensions. Yeah.
Thank you, sir.
Did you understand this?
Yes, sir. Yes, sir.
Okay.
So
Any
I think we can proceed with the session, sir. No, sir.
I want to stop here now. It's almost closing up. So I mean, thing is, I would like to stop at this slide, and if time permits or if something is there, we can go ahead and discuss.
Yes, so actually, the questions related to this is not there.
Any other question? Those are there, can understand. For example, I will show one slide. I will show one slide where, let's say this is, I mean, the moment you understand all this, you would be in a position to understand classification like this. So what is shown in this diagram, I mean, I really, I can understand that. I mean, I have not covered many of things over here, but the thing is, I would like to give some, I mean, interpretation or some, I mean, explanation regarding this figure, right? So whatever you can see that, I mean, over here, right? You can see that there are points which are, I mean, shown by this stars, right? And there are these field circles, right? And there's a hyperplane that is shown. There is this hyperplane that is shown over here. This is the hyperplane, right? This is the margin that we got by designing SVM classifier. And you can see that some of the points are inside this boundary. Some of the points are on this boundary, right? Some of these points, right? You can see that now this point, right? The class of this is above this. So some of the points are misclassified, right? Now you can see that the class of these stars are on this side, right? So this is the, I mean, misclassified point, right? So remember that it is possible to design a classifier which allows some amount of misclassification. So this is misclassification. This is the margin that we can allow, right? And some of all these margins have been specified by summation of xi's, right? So it is possible to design like this, and then we can have parameters. This is the Lagrange coefficient, and this is the margin xi's, and then we can have comments based on that, right? So for example, if alpha 1 for 0.1, this is well below this margin, right? So you can see that this Lagrange coefficient is 0, as well as this margin error is also 0. So this is the correctly classified point, right? But for like look for point number 5, right? Point number 5 over here, point number 5 is still correctly classified, but this alpha 5 is become C, right? Where C is one of the parameter in optimization that we, I mean, I have not covered, right? And this xi 5, the margin is less than 1, right? But remember, consider for point number 8, right? For point number 8, the point is misclassified. If I'm going to have this hyperplane, right? For point 8, the like the sign of this distance is positive, and well beyond this, right? So it is classified as +1 or belonging to this dot class, right? So from this we can clearly understand, right, that alpha 8 is C and psi 8 is 1. So this is misclassified point, right? And such points are referred as bounded support vectors, right? The points which are there on these boundaries are referred as free support vectors, and these are bounded support vectors, right? And moment we design any classifier, we can have these values of alpha i's and psi i's, right? So by knowing these alpha i's and psi i's, we can clearly tell at which points are correctly classified, where is the hyperplane, what are the margins, and everything, right? So to understand this, to understand and to interpret these values, what I think is you need to understand the formulation, you need to understand terms and terminologies in these optimization problem, so that you can interpret this, and you can use a tool. You can use either sklearn or Veka tool or some other tool, wherein those tools are going to give us these values, right? And we must be in a position to interpret these values. That is the thing that we need to understand. From that perspective only, we need to understand all the analytics, all the mathematical terms and terminologies behind support vector machine. Yeah.
Thank you, sir. So the questions are 2-3 questions, but already answered very clearly in your session. So I will not take this. So with this, we are concluding the question answer session also. Thank you very much, sir, for this rigorous mathematical explanation. So I, Dr. Sakshi Paithane, propose vote of thanks to Dr. Bartakke, sir. Thank you very much, sir, for accepting the invitation. And thank you very much, sir, for this explanation with rigorous mathematical approach. With the superficial knowledge, we cannot proceed with the classifier. So with this session, I assure that all the participants had clear their basic knowledge and mathematical thinking about the classifier. Thank you very much, sir.
Okay.
Thank you, sir.
Jadhav sir is there.
Thank you, sir. I'm in the university. Thank you, sir. Bartakke, sir, once again.
I just wanted to give flavor of what is SVM classifier. Just do not use this blindly, right? Now, people, I have seen all the researchers, right, using this SVM classifier very, very blindly, right? And without interpreting the value that it outputs, right? So my aim in, I mean, going into those details is just to make you understand that there is lot of stuff behind all these things, which a researcher has to understand and then interpret the results. Right? That was the effort. Right?
Yes, sir. Definitely, sir.
I really understand that. I mean, if it would have been in like person the session, and then if I got a lot of time, right, we could have gone to any details and understood this, right? But I do not want to miss the opportunity to communicate the message, right? The message must be communicated, right? Things will come, right? Message must have been understood, digested by participants.
Thank you very much, sir. Thank you.
Thank you. Bye.
Thank you, sir.
Thank you.
Yes, participants are requested to leave the meeting. Tomorrow, please join the sessions at 10 o'clock. Thank you all. Good day.